chapter electrochemistry. So basically, if you make this particular chapter strong, your electrochemistry, I'm damn sure that automatically is going to become strong, my dear students. Yeah. So let me know in the chats if you all are super duper excited about this particular session, my dear students. Quickly, let me know in the chats. Till then, let me do some basic things. Yeah. Quickly, let me know in the chats, my dear students, if all of you are again super duper excited for this amazing session. So this session duration will be approximately for like 4 to 5 hours or maybe even more, right? So we shall be completing this chapter today only so that our this week's target is attained properly without any delay. Okay, so that there will be no backlogs for you. Perfect. So let's cover the weekly target by completing the chapter Redox reaction today. Perfect. So this is all about me, right? My name is Wassim Bhat and I'm your chemistry educator here on this particular channel as well as on Unacademy JEE English channel, right? Okay, leaving this aside, the ones who have not liked the session yet, I would want every one of you to like the session. Do share this particular video with everyone. Everyone means whosoever is preparing for NEET 2024 and cannot afford the quality education in the paid batches, right? Cannot afford basically the paid batches. These particular sessions are basically for them. Okay? Because my dear students, whatever we are going to teach you here on this particular channel, there'll be no compromise on the content, right? Whatever content we provide in the paid batches, same content we provide here on YouTube as well. You need not worry about the content at all. Perfect. So that's why I keep on telling you to share all these videos with the students who are going to write the NEET in 2024 or even in 2025, particularly the ones who cannot afford the paid batches. Okay. And at the same time, if you are not subscribed to your channel, right, do it right now, right? Let this family grow even bigger at exponential pace. Okay. Perfect. So let's get going then. Let's get started. The first topic which we are going to cover today, which forms the basis of the chapter, that is going to be the term oxidation state. Yeah. So let's exactly get to know what the term oxidation state is all about and where all we use this particular term. Okay. Whatever I'll be mentioning on the screen, I would want every one of you to take a note of every single thing with me itself. Okay. Perfect, guys. As far as the term oxidation state is concerned, how do we define it? How do we define the term oxidation state? My dear students, oxidation state is simply defined as the charge present on an atom of an element. The charge present on an atom of an element in a given compound. In a given compound. What it means exactly, you'll get the idea in some time. Let me first of all write few important points. Number 2. For ionic compounds, the charge is real. The charge is real. And for covalent compounds, the charge is virtual. The charge is virtual. Next point, oxidation state is defined for one atom of an element. Oxidation state is defined for one atom of an element. Now, let's get to know all these statements in detail so that there'll be no confusion while using the term oxidation state. Yeah? Have a look, guys, what all these points exactly means. Okay? Have a look. My dear students, for example, let's say I'm taking one ionic compound over here. And you all must be knowing what is the common example of the ionic compound. I'm sure majority of you guys will be knowing. What is the common example of the ionic compound? What is the typical example of the ionic compound? Just tell me that. What is the typical example of the ionic compound? You must be knowing the typical example of the ionic compound, that is NaCl. Sodium chloride. It is the typical example of the ionic compound. Absolutely, right? Now, my dear students, in this NaCl, if I ask you, do you see any charge present on sodium? Well, I cannot see any charge present on sodium. I cannot see any charge present on chlorine, right? I cannot see any charge present on sodium. I cannot see any charge present on chlorine. But if you exactly see how this NaCl has got formed, then you'll get to know the charge present on sodium. At the same time, you'll get to know the charge present on chlorine. So first of all, we need to see how this NaCl has got formed. My dear students, you must be knowing one thing. This sodium over here, sodium is the example of a metal, and chlorine, it is the example of the non-metal, right? And metals are considered to be electropositive in nature. Metals are considered to be electropositive in nature. That means metals have got tendency to lose electrons. Perfect. When I talk about the non-metals are generally considered to be electronegative in nature. That means they have got the tendency to gain electrons. They have got the tendency to gain electrons. Now, dear students, this sodium, since it's a metal, it has got high tendency to lose electrons. This chlorine, it's a non-metal. It has got high tendency to gain electrons. Now, you tell me one thing. Which group this sodium belongs to? Sodium belongs to group 1. If I particularly talk about sodium, sodium belongs to group 1. That means in the outermost shell of sodium, you'll just find one electron, right? In the outermost shell of sodium, you'll get only one electron. And since it's highly electropositive, so it has got high tendency to lose that one electron and will get converted into Na positive. So sodium, since it's highly electropositive, so it will be easily losing one electron and getting converted into Na positive. Number 1. Number 2, chlorine over here, which has got the tendency to gain electrons. Since chlorine belongs to halogens, and halogens have got 7 electrons in their outermost shell. So I would say the electron which is given by sodium, chlorine is going to gain that particular electron completely and will get converted into Cl negative. Perfect. The electron which is given by sodium, chlorine is going to gain that one electron completely. Then only it gets converted into Cl negative. Now, my dear students, what has happened? If I ask you what has happened here, what has happened? I would say the formation of cation and anion took place, right? The formation of cation and anion took place. Now you have got Na positive and Cl negative with you. Perfect. Now, dear students, since you have got two equal and oppositely charged species over here, can I say between two equal and oppositely charged species, there will be electrostatic force of attraction? Yes, there will be electrostatic force of attraction. There will be electrostatic force of attraction. And this electrostatic force of attraction between these two oppositely charged species, this is something which we call as ionic bond. This is something which we call as ionic bond. And any such compound in which ionic bond exists, that compound is something which we call as ionic compound. That's what we call as ionic compound. My dear students, either you call it as ionic bond or you can call it as electrovalent bond as well. You can call it as the electrovalent bond as well. Why is that? Why is that? Dear students, can I say complete loss and gain of electrons is taking place here? Sodium is losing one electron completely and chlorine is gaining that one electron completely. Sodium is losing one electron completely and chlorine is gaining that one electron completely. So I must say complete loss and electrons is taking place over here, right? And let me tell you, any bond which gets formed due to complete loss and gain of electrons, that bond is something which you call as electrovalent bond or ionic bond. Perfect. Now, my dear students, if I ask you, actually sodium in NaCl, it exists in the form of Na positive. Chlorine in NaCl, it exists in the form of Cl negative. Now, do you see any charge present on sodium over here? Yes, I can see plus 1 unit of charge on sodium. I can see minus 1 unit of charge on chlorine, and the charge present on an atom of an element that defines its oxidation state. So I must say the oxidation state of sodium right here is plus 1, the oxidation state of chlorine right here is minus 1. That means sodium has lost 1 electron completely and chlorine has gained that 1 electron completely. Perfect. The oxidation state, the charge present on 1 atom of sodium, that's plus 1. The charge present on 1 atom of chlorine, that's minus 1. So these two are something which I'll be calling as the oxidation state. Right? And at the same time, do remember one more thing. Due to complete loss and gain of electrons, due to complete loss and gain of electrons, due to complete loss and gain of electrons, the charges on the elements, the charges on the elements are real. Do remember, whenever charges appear on an element, whenever charges appear on the atom, due to complete loss and gain of electrons, these are basically at that time called as the real charges. These are the actual charges. So this plus 1 actually indicates that sodium has lost 1 electron completely. Chlorine has gained 1 electron completely. And due to complete loss and gain of electrons, whatever charges come on the atoms, those are always the real charges. Those are not the virtual charges. These are the real charges. Okay? I hope you got to know the meaning of the oxidation state. The charge present on 1 atom of an element. As simple as that. Okay? Now, dear students, if you talk about the covalent compounds, covalent compounds, right? We have got some typical examples of the covalent compound, wherein covalent bonds exist, right? Let me not go there. For example, I have got a bond between A and B. I have got a covalent bond between A and B. Perfect. At the same time, I'm assuming that electronegativity of B is greater than that of electronegativity of A. Now you tell me. Since there's a covalent bond in between, so I'm assuming that the electron pair, the bonded pair of electron, should be at the center, right? Since it's a covalent bond formed by mutual sharing of electrons. So this particular electron pair over here, it has to be at the center. But I'm assuming electronegativity of B is more than that of A. What does that mean? That means B has got more tendency to attract the bonded pair of electron towards itself. Dear students, if B has got more tendency to attract the bonded pair of electron towards itself, and I say electron density towards B will be increased and electron density towards A, that will decrease. Let me tell you, the increase in the electron density towards B is represented by delta negative. The decrease in the electronegativity towards A, that's something which we represent with delta positive. Perfect? Right? So my dear students, if I ask you, is here complete loss and gain of electrons taking place? Complete loss and gain of electrons is not taking place here in this case. It is just shifting of electron pair is taking place. And due to the shifting of electron pair, whatever charges come on these atoms, these are not the actual charges, these are not the real charges, these are the partial charges. These are the virtual charges, right? These are the virtual charges. If you ask me, what is the oxidation state of A over here? I'll say plus 1. What is the oxidation state of B over here? I'll say minus 1. But does that mean this A has lost 1 electron completely? No. Does that mean this B has gained 1 electron completely? Absolutely not. Right? It just tells you that the electron pair has been shifted towards B. That's it. Yeah? So do remember, due to the shifting of bonded pair, due to the shifting of electron pair, whatever charges come on the atoms, they are not the real charges, they are the virtual charges. So let me point out one simple thing over here. Virtual charges on the atoms. Virtual charges on the atoms arise due to electronegativity difference. Due to electronegativity difference between the atoms. electronegativity difference between the bonded atoms. I hope it's super clear to you. Okay, point number one. Point number two. Let's say I do not have a single bond between A and B. Let's say I have a double bond. Let's say I have a double bond between A and B. And I'm assuming again that electronegativity of B is greater than that of electronegativity of A. Now people, if B is more electronegative, so B has got more tendency to attract the bonded pair towards itself, right? So how many bonded pairs are right now in between? There are two bonded pairs. Now this B is going to attract both the bonded pairs towards itself, due to which this B gets minus 2 delta and this A gets plus 2 delta. Now if I ask you, what is the oxidation state of A over here? You will say plus 2. What is the oxidation state of B over here? You will say minus 2. But does that mean this A has lost 2 electrons completely? No. Does that mean B has gained 2 electrons completely? No. Right? What does this plus 2 mean then? What does this minus 2 mean then? Are these not the real charges? No, these are the virtual charges. These are the charges which appear to be present on the element, on the atom. Simply, since B is more electronegative and it has attracted both the bonded pairs towards itself, right? So minus 2 signifies that B has attracted both the bonded pairs towards itself. Similarly, plus 2. Yeah? One last example. For example, you have got a triple bond between A and B. Let's say you have got a triple bond between A and B. Again, I'm assuming that B is more electronegative. So what will happen? This will have minus 3 delta. This will have plus 3 delta. So the oxidation state of A over here is plus 3. The oxidation state of B over here is minus 3. Now you tell me, are these real charges or virtual charges? Quickly. These are imaginary charges, right? These are virtual charges, right? They happen to be present on the atoms due to what? Due to electronegativity difference between the bonded atoms, right? It simply tells you, this minus 3 simply tells you that B has attracted all the 3 bonded pair of electrons towards itself. That's all. So my dear students, one simple thing which I would want you guys to remember. Whenever you talk about ionic compounds, in ionic compounds there is complete loss and gain of electrons. And due to complete loss and gain of electrons, whatever charges arise on the atoms, they are always going to be the real charges. In case of covalent compounds, whatever charges will be there on the atoms, they are always going to be virtual charges, right? Which happen to be present on the atoms due to electronegativity difference. I hope this is super clear to you. Yeah. For example, let me give you quick examples of this particular one. Since you know, in your periodic table, chlorine is more electronegative than oxygen. Oxygen is more electronegative than nitrogen. You know it? Perfect. One thing. Number two, you must be knowing one more thing. On moving from left to right, in the periodic table, generally, what happens to electronegativity? Generally, electronegativity increases. Perfect. On moving from left to right, generally, electronegativity increases. Similarly, on moving from top to bottom, generally, electronegativity decreases. This is something which I would want you all to remember. Okay? Everything clear till here? Everything clear till here, my dear students? Yeah? Say yes or no in the chats quickly. I want the chat box to be moving continuously, guys. I want the chat box to be moving continuously. Okay, one more thing which I would want to present. What is that? See, for example, I'm talking about water. Let's say I've got water, right? I've got water over here. Do you know the structure of water? You must have studied somewhere. Anyways, next week I'm going to teach you chemical bonding. You need not worry about the structures at all. Okay? So since I'm taking water into consideration over here. Now, my dear students, if you talk about this particular bond between oxygen and hydrogen, which one is more electronegative? Oxygen. So this bonded pair will be shifted towards oxygen, due to which oxygen gets minus delta, hydrogen gets plus delta. Talking about this particular bond, again, oxygen is going to attract this bonded pair towards itself, so minus delta, and this is plus delta. Perfect. Now, if I ask you, what is the oxidation state of this particular hydrogen? You'll say plus 1. What is the oxidation state of this particular hydrogen? You'll say plus 1. What is the oxidation state of this particular oxygen? You'll say minus 2. Right? Now, how do you mention it? How do you mention it? You'll be writing it like this. H 2O, right? Oxygen, its oxidation state is -2 at the top of it. Hydrogen, its oxidation state. What is the oxidation state of hydrogen? Don't do like this, +1 + 1 is +2. No. Oxidation state is defined for one atom of an element. If I'm asking you, what is the oxidation state of hydrogen in water? That means I'm asking you, what is the charge present on one atom of hydrogen? That means I'm asking you, what is the charge present on one atom of hydrogen? And charge present on one atom of hydrogen is basically +1. Okay, that's why I wrote one statement. Oxidation state is defined for one atom of an element. Perfect. Is this clear? Similarly, if I take one more example, let's say I'm talking about NH3. I'm talking about NH3. All of you must be knowing its structure. This is N, this is H, this is H, and this is one more H, right? So directly I'll say the oxidation state of this hydrogen is +1, this is +1, this is +1, and nitrogen, it's -3. Now, how do you write it? That is the point. You'll write NH3. Perfect. The charge present on nitrogen. The charge present on nitrogen, that's -3. Perfect. If I ask you what is the oxidation state of hydrogen in this compound, that means I'm asking you what is the charge present on one atom of hydrogen, and the charge present on one atom of hydrogen is +1. Perfect. I hope all these things are super duper clear to you. So quickly, let me know in the chats with the thumbs ups if you got to know the basics of what oxidation state is, what is meant by it, when is it real, when is it imaginary or virtual, right? In which compounds it is real, in which compounds it's virtual, right? All these things, if you got to know properly, then quickly let me know in the chats. Everyone. Everyone, people. By the way, you'll be getting the PDF of this particular session on the Telegram group afterwards, which is t.me/WASSIMSIRCHEM. This is the Telegram channel. You'll be getting the PDF, handwritten PDF of this particular session in the Telegram group at the end. Okay? Now, guys, understand. There are some rules by means of which we calculate oxidation states of different elements. Some rules are there, basically. Okay? Let's have a look. Let's have a look what exactly those rules are. And you are going to remember those rules from now on. Yeah? Perfect. So rules to calculate oxidation state. The first rule, the oxidation state of an element, in its standard state is taken to be zero. The oxidation state of an element in its standard state is taken to be zero. Now you must be thinking, what is meant by standard state of an element? Let me tell you, standard state is that state of the element in which element exists in nature. In short, standard state is the most stable state of the element thermodynamically. For example, oxygen in nature exists in the form of O2 gas. Hydrogen in nature exists in the form of H2 gas. Chlorine in nature exists in the form of Cl2 gas. Iron in nature exists in the form of Fe solid, right? Zinc in nature exists in the form of zinc solid, right? So I would say this O2 gas, this is the standard state of oxygen. H2 gas, it is the standard state of hydrogen. This is the standard state of chlorine, standard state of iron, standard state of zinc. Perfect. And whenever element exists, whenever element is present in its standard state, its oxidation state directly is taken to be zero. Perfect. Now, my dear students, that particular element which has got allotropes, for example, I've got an element, it has got two allotropes, allotrop 1, allotrop 2, right? That particular allotrop which is thermodynamically more stable, is considered to be the standard state of the element. So let me write this statement over here, then I'll make you understand what it means. I'm writing the statement right here. That allotrop of an element which is thermodynamically more stable. which is thermodynamically more stable, is considered to be the standard state. Is considered to be the standard state of the element. For example, if I talk about carbon, right? Carbon. Its two main allotropes, you all must be knowing. One is diamond, and one is graphite. Perfect. These are the two main allotropes of carbon. Now, my dear students, if I ask you which allotrope is thermodynamically more stable, diamond or graphite? What do you think? Which allotrope is thermodynamically more stable? Diamond or graphite? Can you let me know quickly in the chats? See, a lot of you must be thinking that diamond is thermodynamically more stable, but it's not diamond, it's graphite, which is thermodynamically more stable than that of diamond. So if graphite is thermodynamically more stable, then I would say the standard state of carbon, is going to be carbon graphite. This is the standard state of carbon. Carbon graphite is the standard state of carbon. Now you all must be thinking, why this graphite is more stable? Why this graphite is more stable than diamond thermodynamically? Let's get to know about this as well, right? Because we have got time. Perfect. So it's better to learn things with the help of concepts. No need to remember things right now. Okay. Let's try to understand first of all why graphite is more stable. Why graphite is thermodynamically more stable. More stable than diamond, right? Let's get to know about this. See guys, on one side, I'm writing graphite. On another side, I'm writing diamond. Okay. Now, as you all must be familiar with the fact that in case of graphite, every carbon is attached to 4 other carbon atoms. Every carbon is attached to 4 other carbon atoms in case of what? Sorry, in case of diamond. Wait, I reversed it. Just a second, sorry. I'm talking about the diamond. In case of diamond, every carbon is attached to 4 other carbon atoms. Right? Every carbon is attached to 4 other carbon atoms. Perfect. You know it. If I ask you, how many valence electrons are there with carbon? Carbon has got 4 valence electrons. Can I say carbon is using all its 4 electrons to form bonds? Yes, carbon is using all its 4 electrons to form bonds. That means, will there be any free electron with this carbon? No. Will there be any free electron with this carbon? No way. Right? No free electrons over here. But in case of graphite, as you all must be knowing, graphite has got the layered structure. It has got the layered structure. And how it looks like? Have a look. I'm just going to draw one layer. over here. I'm just going to draw one particular layer over here. That's all. Okay, this is one layer of graphite. Similarly, there will be one more layer of graphite, and between the layers, there will be van der Waals force of attraction. No need to go about that. Right? Have a look, people. Understand now. For example, if I talk about this particular carbon, this carbon is bonded to 3 other carbon atoms. 1, 2, 3. It is bonded to 3 other carbon atoms. Now, we already know, if I talk about carbon has got 4 valence electrons, right? Carbon has got 4 valence electrons. Now, out of 4 valence electrons, this carbon is using 3 electrons to form bonds. So there'll be 1 electron left on carbon as such, left on this carbon as such. Every carbon will be having 1 electron. Absolutely. Every carbon is having 1 electron. Now, my dear students, if every carbon is having 1 electron, can I say here this electron can form a bond? Here this electron can form a bond. This one and this one can form a bond. This one and this one can form a bond. These two 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 also. Perfect. So what do you see something new here? What do you see something? I'll say I'm seeing alternate sigma pi conjugation. Pi, sigma, pi, pi, sigma, etc. I'm seeing alternate pi, sigma conjugation. Pi, sigma, pi, right? Sigma, pi, alternate pi, sigma conjugation. And due to alternate pi, sigma conjugation, can I say there are chances of resonance in graphite? There are chances of resonance in graphite. Absolutely, there are chances of resonance. And due to resonance, due to the probability of showing resonance, whenever resonance exists in a molecule, what happens? Stability of that increases, right? So that is the reason why graphite is considered to be more stable than that of diamond thermodynamically. The reason is because in graphite, there is the chance of resonance, and we know resonance increases the stability of the molecule. I hope this is clear to everyone. Okay. So I was basically talking about the rules. The first rule was whenever the element is present in its standard state, its oxidation state will be taken as 0. Number 1. Rule number 2. When you talk about your group first elements means alkali metals. Group first elements. Group second elements are your alkaline earth metals. Perfect. Alkali metals, what do they have? They have got only one electron in their outermost shell. Yeah? Perfect. They have got only one electron in their outermost shell. So they can easily lose that one electron. And when the atom loses one electron, they get +1 charge. Do remember from now onwards, all the alkali metals, whenever you see the alkali metals in any compound, do remember its oxidation state will be taken as +1. Similarly, my dear students, when you talk about the alkaline earth metals, since they have got 2 electrons in their outermost shell, so they can easily lose them, right? So they'll show +2 oxidation state all the time. Alkali metals, all the time they'll be showing +1 oxidation state. Alkaline earth metals, they'll be showing +2 oxidation state all the time. Yeah? Perfect. Now people, talking about one more rule that is related to hydrogen. See guys, the oxidation state of hydrogen is generally taken as +1 when attached to more electronegative element, but when attached to less electronegative element, its oxidation state is taken as -1. What does that mean? Say, let me write the things very simpler, in the very simpler way for you. For example, I've got hydrogen. Let's say hydrogen is attached to more electronegative element than itself. Let's say we have got a compound in which hydrogen is attached to more electronegative element than itself. Whenever you see hydrogen attached to more electronegative element than itself, its oxidation state directly you'll be taking as +1. For example, you have got HCl, hydrogen attached to more electronegative element. The oxidation state of hydrogen here is +1. Here it will be +1. Here it will be +1. So wherever you see hydrogen attached to more electronegative element than itself, its oxidation state will be taken as +1. But when you see hydrogen attached to less electronegative element than itself, when you see hydrogen attached to less electronegative element than itself, the oxidation state of hydrogen will be taken as -1. Now, which elements are less electronegative than hydrogen? Which elements are less electronegative than hydrogen? All your group first elements and group second elements. Your group first elements and group second elements, they are comparatively less electronegative than that of what? Than that of hydrogen. Now see over here, in case of NaH, hydrogen is attached to group 1 element. Hydrogen is attached to less electronegative element than itself. So oxidation state of hydrogen is -1. For example, you have got one more example, MgH2. Hydrogen is attached to group second element. Hydrogen is attached to less electronegative element than itself. So its oxidation state directly -1. Okay. So hydrogen, when attached to less electronegative element than itself, so its oxidation state at that point of time will be taken as -1. Okay. Now talking about oxygen. What about oxygen? Few more rules are left, then the chapter will become interesting. Just wait for it. I know this is all a little boring, right? Because you have to remember things right here. Okay, talking about the oxidation state of oxygen. Oxidation state of oxygen, it is generally taken as -2. But when attached to less electronegative element than itself. For example, you have got MgO. Oxygen is attached to less electronegative element than itself. So I would directly say oxidation state of oxygen is -2. Na2. Oxygen attached to less electronegative element than itself. Oxidation state -2. Water, H2O. Oxygen attached to less electronegative element than itself. Again -2. So whenever you see oxygen attached to less electronegative element than itself, generally its oxidation state will be taken as -2. Number one. Are there some exceptions? Yes, there are some exceptions. Peroxides, superoxides, and oxyfluorides. These are some compounds which oxygen forms. These are some compounds which oxygen forms, right? Now let's talk about peroxides first. See, when you talk about the peroxide, what is a peroxide basically? First of all, whenever you see oxygen in this situation, oxygen, single bond oxygen, whenever you see oxygen, when you see a single bonded linkage between two oxygen atoms, when you see a single bonded linkage between two oxygen atoms, this single bonded linkage is what we call as peroxide linkage. This is something which you call as peroxide linkage. This is something which you call as peroxide linkage. And in any compound, if this peroxide linkage exists, we call that compound directly as peroxide. That compound in which peroxide linkage exists, that's what you call as peroxide. For example, you have got hydrogen peroxide. You have got H2O2. If you remember what is the structure of H2O2, it has got an open book-like structure. This is H, this is H. This is the structure of H2O2. Now, my dear students, understand few things. This single bond between oxygen and hydrogen, the bonded pair will be shifted towards oxygen, due to which it gets -1, hydrogen gets +1. What about this particular bond? Again -1, +1. What about this bond in between? Nothing will happen due to this bond, because on one side you have got oxygen, on another side also you have got oxygen. So the electron pair over here is exactly going to be at the center. So if I ask you, is this a peroxide linkage? Yes, it's a single bonded linkage between two oxygen atoms. So it's a peroxide linkage. It's a peroxide linkage. I'll be calling this compound as peroxide. Now, what is the charge present on one oxygen atom? -1. What is the charge present on one oxygen atom? -1. So can I say, when oxygen forms the peroxides, its oxidation state will be taken as -1. There is one exception as well, which I'll be telling you later. Is this clear to everyone? So, in case of peroxides, the oxidation state of oxygen is -1. Right? Now, in case of superoxides, what are superoxides? Whenever you see oxygen present in the form of O2 negative, for example, you have got KO2. You have got KO2, right? This potassium is group 1 element, and it will show plus oxygen state, +1. So if I leave this K positive aside, that means there will be minus charge over here. I've taken K positive out, so it becomes O2 negative. Initially it was KO2. Now I've taken K positive out. Now it becomes O2 negative. Whenever you see oxygen in this form, O2 negative form, this is something we call as superoxide. And in case of superoxides, the oxidation state of oxygen is taken as -1/2. See, one thing I told you a few minutes back. Oxidation state is the charge present on one atom of an element. Over here, on two atoms of oxygen, the charge is -1. On two atoms of oxygen, the charge is -1. That means on one atom of oxygen, the charge will be -1/2. On two atoms of oxygen, the charge is -1. That means on one atom of oxygen, the charge will be -1/2. So -1/2 is the oxidation state of oxygen in case of what? In case of superoxides like KO2. Okay. Now there are a few more compounds as well, which you call as oxyfluorides. In case of oxyfluorides, oxygen can show positive oxidation state as well. In case of oxyfluorides, oxygen can show positive oxidation states as well. Okay, have a look. If I talk about OF2, this is your OF2, right? Similarly, you have got O2F2. These are your oxyfluorides. Now, my dear students, understand one thing, one simple thing. There is a single bond between oxygen and fluorine. Which one is more electronegative? Fluorine. So it will have -1, oxygen will have +1. Again, single bond, -1, +1. If I ask you, what is the total charge present in oxygen here? You'll say +2. So +2 is the oxidation state of oxygen in OF2. Similarly, have a look over here on this structure. This is OF, -1, +1. Again, a single bond, -1, +1. Here you have got a peroxide linkage, single bonded linkage. Nothing will happen due to this linkage, right? So the oxidation state of oxygen here is +1. Perfect. Perfect, guys. So is it necessary that when oxygen forms peroxide, its oxidation state will be always -1 only? No, it can be +1 also, as you saw in case of O2F2. I hope it's again clear to everyone. Yeah? Is this clear till here? Quickly in the chats. This is all basics. See, what I taught you a few minutes back, I told you in case of peroxides, oxidation state is -1. But here also you're got a peroxide, right? It's a single bond between two oxygen atoms, but its oxidation state is +1. Okay? Perfect. So generally, when you talk about oxygen generally, when it will be attached to less electronegative element than itself, its oxidation state generally will be taken as -2, right? When it forms peroxide, it can be -1. When it forms superoxides, it's going to be -1/2. When it forms oxyfluorides, it can be +1 or +2, as you saw in OF2 and O2F2. Perfect. These are some special things. These are some special things which you need to know about the element oxygen. Okay. Now, guys, there is something about halogens as well. So first we discussed about hydrogen, then we discussed about oxygen. Now it's time to get something about halogens as well. If I talk about halogens, halogens are your group 17 elements. Group 17 elements, fluorine, chlorine, bromine, iodine, S2T. Halogens, they are generally going to show -1 oxidation state when attached to less electronegative element than itself. Talk about chlorine, talk about fluorine, talk about bromine, attached to less electronegative element than itself. So directly, its oxidation state -1. Here, -1. Here, -1. So when you see halogen attached to less electronegative element than itself, you'll be directly taking its oxidation state as -1, right? Can halogens show positive oxidation states as well? Yes, they can show positive oxidation states. There are some compounds wherein they can show positive oxidation states. For example, you have got Cl2O, you have got IF5, you have got IF7, you have got, for example, ClF3. You have got ClF3. These are different compounds wherein halogen can show positive oxidation state as well. Now understand, ClO2 will be something like this. This is ClO2. IF5, this is iodine, this is F, this is F, this is F, one more F, and one more F. I'm drawing the rough structure. Similarly, IF7, 7 fluorine atoms, 1, 2, 3, 4, 5, 6, 7. It's not the actual structure though, it's a rough structure. Okay. ClF3, it's rough structure, 3 fluorine, correct? Now, my dear students, if you talk about the first compound, Cl2O, talk about this particular oxygen. The bond is between oxygen and chlorine. Which one is more electronegative? Which one is more electronegative? Oxygen. So this bonded pair will be shifted towards oxygen, so -1 at the same time +1. This bonded pair will be shifted towards oxygen, -1 at the same time +1. So what is the charge present on chlorine over here? Chlorine is the halogen, and the charge present on one chlorine atom, that's +1. So oxidation state of chlorine here comes out to be +1, right? Perfect. Similarly, talk about the second one. The oxidation state of iodine over here will be +5 because it's attached to 5 fluorine atoms. So it will be directly +5, again positive. Again, the halogen, which I'm underlining over here, it's showing plus oxidation state. Here, the halogen which I've underlined, it's showing plus oxidation state. Again here, the halogen which I'm underlining, it is showing +7 oxidation state. Again, the halogen which I'm underlining, it is showing +3 oxidation state. So, does that mean halogens, they always show negative oxidation state? No. They can show positive oxidation state as well, as you saw in different compounds like your Cl2, IF5, IF7, and ClF3. I hope it's clear to you. Quickly, let me know in the chats. Quickly, let me know in the chats, people. Let me know in the chats quickly if it's clear. Quickly, let me know in the chats with the thumbs ups. This is all basics which I'm teaching you related to the oxidation state. Perfect. There is something called as radicals. This is one more rule. Radicals. It's not the Free radicals which you study in organic. Radical simply means any atom or group of atoms which has got charge on it. That's something which we call as a radical. So what is a radical first of all? An atom or group of atoms. An atom or group of atoms having charge. Having charge are called as radicals. Any atom or group of atoms which have got charge on it, they are termed as radical. And let me tell you, there is a special treatment with radicals basically. Radicals are considered as a single unit. They are considered as a single unit. And whatever charge is present on the radical, that's considered to be its oxidation state. What does that mean? Have a look. See guys, starting for example with O di-negative. Charge, atom carrying the charge. So it's a radical. So radical is considered as one unit. And whatever is the charge present on it, that's considered to be its oxidation state. So oxidation state of oxygen in O2 negative is -2. Oxidation state of nitrogen in N3 negative is -3. Oxidation state of phosphorus in P3 negative is -3. Right? Similarly, S di-negative, it's -2. Talking about group of atoms. Group of atoms having charge, right? So this OH over here, it's a radical basically OH negative. But this OH, this radical, it will be considered as a single unit. And the charge present on it is considered to be its oxidation state. So here I'll say the oxidation state of OH is -1. Pn negative, again group of atoms having charge. So it will be considered as a single unit. Now right here I'll say the oxidation state of Cn is -1. The oxidation state of NC is -1. The oxidation state of SO4 is -2. The oxidation state of SO3 is -2. Right? Similarly, oxidation state of PO4 is -3. Oxidation state of PO3 is -3. Oxidation state of oxalate is -2. S2O3 di-negative, right? S4O6 is -2. So in short, just remember one thing. In short, just remember one thing. Radicals are atoms or group of atoms having charge on them, right? And radicals are considered to be a single unit. And whatever charge is present on the radical, that is considered to be its oxidation state, right? Directly, I'm considering this radical as a single unit. And that's why I'm saying the oxidation state of PO3 is -3. I'm considering it as a single unit. Perfect? Right, people? Similarly, you have got NH4 positive. It's a radical. Perfect. Charge is +1. So I'll say the oxidation state of NH4 in NH4 positive is +1. The oxidation state of NO over here is +1. Perfect. So these were some basic rules which you need to know about the oxidation state. Okay. Now the chapter is going to become interesting. Perfect. Till now, there were things which you had to remember. Now, no need to remember anything. Just apply all these things in the questions. Okay. This is one important statement. The sum of oxidation states of all the elements, the sum of oxidation states of all the elements present in a molecule is always equal to the net charge present on the molecule. What does it mean? The sum of oxidation states of all the elements present in a molecule is equal to the net charge present on the molecule. What does that mean? Let's have a look. For example, you have got Cr2O7 di-negative. And I want you to calculate the oxidation state of chromium over here. How exactly you are going to do it? Let's assume the oxidation state of chromium is X. Let's assume the oxidation state of chromium is X. But over here, there are 2 chromium atoms. So it becomes 2X plus. Oxidation state of oxygen, generally taken as -2. How many oxygen atoms are there? 7 oxygen atoms. Is there net charge present on the molecule? Yes, it's -2. Just solve the equation. Get the value of X. X value will come out to be +6. So +6 is the oxidation state of chromium in Cr2O7 di-negative. Right? S2O3 di-negative. Calculate the oxidation state of sulfur. Let's assume the oxidation state of sulfur is X. So it becomes 2 times X plus oxygen will form -2 oxygen state and there are 3 oxygen atoms. Net charge present on it is -2, right? Just solve it. How much the value will be? Quickly, how much the value will be? It will be +2. So +2 is the value of X which you will get over here. As simple as that. NH4 positive. Calculate the oxidation state of nitrogen. Assume that it's X. Hydrogen is attached to more electronegative element than itself. So its oxidation state is +1. Since there are 4 hydrogen atoms, net charge is +1. So get the value of X, it will be -3. Perfect. Calculate the oxidation state of chlorine here. Assume that it's X. Oxygen will show -2 oxygen state. There are 4 oxygen atoms. Net charge is -1. So chlorine will show +7 oxidation state here. X value will be +7. Similarly, talk about this Cr, right? Its oxidation state is X. Oxygen will show -2. There are 4 oxygen atoms. Net charge is -2. The value of X will be getting as +6. So +6 is the oxidation state of chromium over here, right? Perfect. Talk about a few more things. Fe2O3. Oxidation state of iron. Find it out. It'll be just +3. It'll be just +3. Right? Fe3O4. Calculate it. Assume that iron has got X oxidation state. There are 3 iron atoms, so 3X. Oxygen will show -2. There are 4 oxygen atoms. Net charge is 0. So it will have +8/3 oxidation state. Okay. Talk about this particular iron. Talk about this particular iron, right? This particular iron, assume that its oxidation state is X. This is Cn. And Cn, it's basically Cn negative. It's a radical. And radicals are considered to be a single unit. And whatever charge is present on the radical, that's considered to be its oxidation state. So Cn, its oxidation state is -1. And how many Cn are there? There are 6 Cns, right? Net charge is -3. Get the value of X, it will be +3. Perfect. Let me tell you this CO carbonyl. It's a neutral ligand. It's a neutral ligand basically, CO. It does not have any charge. If it does not have any charge, so nickel will have 0 oxidation state. Talk about this sulfur, starting with hydrogen. Hydrogen will show +1 oxidation state. There are 2 hydrogen atoms. Let's assume the oxidation state of sulfur is X. Similarly, oxidation state of oxygen will be -2. There are 4 oxygen atoms. Net charge is 0. So X value over here comes out to be +6. So +6 is the oxidation state of sulfur in case of H2SO4. Perfect. Perfect, guys. So this is how basically you calculate the oxidation states of different elements in a compound. Simple. Sum of oxidation states of all the elements in a molecule is equal to the net charge. Okay. Now over here, as you can see, we have got NH4NO2 over here. NH4NO2. Now understand. Here we have got 2 nitrogen atoms. I want you to calculate the oxidation state of both these nitrogen atoms individually. Now this NH4NO2, it exists in the form of NH4 positive dot NO2 negative. It exists in this format. This NH4NO2, it exists as NH4 positive dot NO2 negative. Now you do one thing, calculate the oxidation states of both these nitrogens. Okay, let's assume that this is one single unit. Let's assume that this is one single unit. The oxidation state of this nitrogen, for example, is X. Hydrogen will show +1. There are 4 hydrogen atoms. Net charge over here is +1. The value of X is -3 over here. So nitrogen will have -3 oxidation state. This particular nitrogen. What about the other one? Assume that it's X. Oxygen will show -2 oxygen state. There are 2 oxygen atoms. Net charge is -1. Get the value of X. X value will come out to be +3. So this particular nitrogen, it is showing +3 oxidation state. As simple as that. Ki3. Get the oxidation state of iodine. Start with potassium. Potassium is a group first element, so +1. +1. Iodine, its oxidation state is X, so 3X. Net charge 0. So X value will come out to be -1/3. So oxidation state of iodine is equal to -1/3. So I hope you can do all these things from now on. For example, you have got C3O2. Tell me the oxidation state of carbon over here. For example, you have got Br3O8. Just tell me the oxidation state of bromine over here. Quickly. For example, you have got Fe 0.98 and O. Tell me the oxidation state of iron over here. You should be able to do this. You should be able to do this, my dear students. Have a look. Assume that it's X, so it becomes 3X. Oxygen will show -2 oxygen state. There are 2 oxygen atoms. Net charge 0. So X value will come out to be +4/3. So +4/3 is the oxidation state of carbon over here, right? Similarly, it will be +16/3. It will be the oxidation state of bromine over here. Similarly, assume that the oxidation state of iron is X. And how many iron atoms? 0.98. 0.98 plus Oxygen will show -2 oxygen state. So net charge is 0. Get the value of X from here. And let me tell you, X value will come out to be plus 200 divided by 98. Plus 200 divided by 98. This is the oxidation state of iron in this particular compound. Is this clear to everyone? Quickly in the chats. Quickly in the chats, people. Every one of you. Sir, KMNO4. Okay, KMNO4. Talk about KMNO4. Get the oxidation state of manganese over here. Potassium, it is a group first element, so +1. Manganese, its oxidation state is X. Oxygen will show -2. There are 4 oxygen atoms. Net charge on the compound is 0. So X value after solving comes out to be +7. So +7 is the oxidation state of manganese in KMNO4. As simple as that. Yeah? Perfect. Now guys, since you got to know how do we calculate the oxidation state with the help of formula, correct? There is one statement which I would want you guys to take a note of. One very important statement. Take a note of this particular statement. I'm writing the term the oxidation state of an element. The oxidation state of an element can never be greater than. The oxidation state of an element can never be greater than +7. Except osmium in osmium tetroxide, OSO4. This was once asked in your AIMS examination as well. What is the oxidation state of osmium in OSO4? It is +8. It is +8. Do remember this statement. Oxidation state of an element, it can never be greater than +7. There is one exception, that is osmium, when it forms osmium tetroxide, where it shows +8 oxidation state. Why am I giving you this particular statement? There is a reason for that. There is a reason for that. My dear students, if I take the compound CrO5 and I'm asking you to calculate the oxidation state of chromium with the help of formula, can you do that? Can you do that? I'm asking you to calculate the oxidation state of chromium here with the help of formula. Can you do that? With the help of formula, I'm saying. What do you think? What do you think? Quickly. Jyoti, that will be done also. Just wait. Just wait. It's simple. Say, you'll assume that the oxidation state of chromium is X. Oxygen will show -2 oxygen state. There are 5 oxygen atoms. Net charge is 0. So the value of X comes out to be +10. Right? So the value of X comes out to be +10. So +10 has to be the oxidation state of chromium. But oxidation state, it can not be greater than +7, except osmium in OSO4. That means there is some mistake which we are committing over here. There is some mistake which we are doing. Now, dear students, remember one particular thing. Whenever with the help of formula, oxidation state of an element comes out to be greater than +7, at that time, you'll be consulting the structure of the compound. Whenever with the help of formula, if the oxidation state of an element comes out to be greater than +7, at that point of time, you'll be consulting the structure of the compound. Now, there are some important structures which you need to remember from now onwards. So, I'm marking the heading as structures of important compounds. Structures of some important compounds, which you must remember from now on. Structures of some important compounds, which you must remember from now on. All right. The first structure, my dear students, that is for chromium pentoxide, CrO5. CrO5. Let's have a look about its structure. Exactly. This CrO5, let me first of all tell you, it has got a butterfly structure. It has got a butterfly-like structure, number one. Number two, it is deep blue in color as well. It's deep blue in color as well. Do remember this particular thing as well. Now, if you talk about the structure of this CrO5, this is Cr. What's happening to the screen? Okay, CrO5. This is chromium over here. There is a double bond. This is oxygen, oxygen attached on this side. Oxygen, oxygen attached on this side. This is the structure of your CrO5. Now, with the help of structure, how will you get to know the oxidation state of chromium? The actual oxidation state of chromium. Have a look. There is a double bond between chromium and oxygen. And oxygen is more electronegative. So, it will attract both the bonded pairs towards itself. So, -2. And due to the double bond, it will be +2. It will be +2. Have a look on this particular single bond between chromium and oxygen. The bond pair will be shifted towards oxygen. So, this will show -1. This will again show +1. This will show -1. This will show +1. Due to this bond, -1, +1. Due to this bond, again -1, +1. If I ask you, what is the net charge present on chromium over here? Check it out. +2, +3, +4, +5, +6. The net charge present on chromium here is +6. The net charge present on chromium here is +6. So I must say the oxidation state of chromium here is +6 in case of CrO5. This is the first question. Second question. How many peroxide linkages do you see in CrO5? How many peroxide linkages? This is one peroxide linkage between two oxygen atoms. This is one more peroxide linkage. So number of peroxide linkages in CrO5, that is 2. That is 2. How many oxygen atoms are there with -1 oxidation states? Whenever you have to calculate the number of oxygen atoms with -1 oxidation state, you will just calculate it like this. Number of peroxide linkages multiplied by 2. So it comes out to be 4. So out of 5 oxygen atoms, there will be 4 oxygen atoms which will be having the oxidation state of -1. Right? As you can see, this one, this one, this one, and this one. And this particular one, it has got -2. So this was our first compound, that is CrO5. It is a butterfly type structure. It is deep blue in color. At the same time, oxidation state of chromium is +6. There are 2 peroxide linkages. There are 4 oxygen atoms with the oxidation state -1 in case of your CrO5. This was our first structure. The second one, H2SO5. You call it as the Carose acid. H2SO5. You call it as the Carose acid. How it looks like. This is sulfur. Double bond O. Double bond O. Oxygen attached with hydrogen. Oxygen attached with oxygen attached with hydrogen. This is H2S1, 2, 3, 4, 5. This is H2SO5. Now let's calculate the oxidation state of sulfur over here. There is a double bond between sulfur and oxygen. We know oxygen is more electronegative than sulfur. So it will have -2. At the same time, it will have +2. Due to this double bond, this will have -2. This will have +2. Due to this single bond, -1. And this will have +1. Due to this single bond, -1 and +1. Now tell me the total charge present on sulfur here. It will be +6. So +6 is the oxidation state of sulfur in H2SO5. Is there any peroxide linkage? Yes, there is peroxide linkage. Oxygen, single bond oxygen. So how many peroxide linkages are there? There is 1 peroxide linkage. How many oxygen atoms are there with the oxidation state -2? Sorry, -1. It's going to be 2. Okay. So this was your H2SO5. Now, the third one. The third one is H2S2O7, which is what you call as oleum. How this oleum exactly looks like? Let's have a look. This is sulfur, oxygen, sulfur. Double bond O, double bond O, oxygen attached with hydrogen. This is double bond, this is double bond, this is oxygen attached with hydrogen. This is the structure of your H2S2O7. And my dear students, let's calculate the oxidation states of sulfur. Talk about this particular sulfur and talk about this particular sulfur. And let's check it out. S double bond O. So -2 +2. S double bond O -2 +2. S single bond O -1 +1. S single bond O -1 +1. What is the total charge present on this sulfur? It is +6. Similarly, what will be the total charge present on this sulfur? It will be +6. since there are two sulfur atoms, one sulfur is showing +6, another sulfur is also showing +6. Now here, I'll be calculating the average oxidation state of sulfur. Average oxidation state of sulfur. One sulfur atom is showing +6, another one is also showing +6, divided by two sulfur atoms. So the average oxidation state of sulfur also comes out to be +6. Yes? Perfect. So this was your oleum. Now, my dear students, after oleum, let's have a look on a few more structures. This is our fourth one. H2S2O8, which is something you call as Marshall's acid. This is something you call as Marshall's acid. Okay? How it looks like. S. This is O. This is O. This again one more S. Double bond O. Double bond O. This is OH. Similarly, this is double bond O. Double bond O. This is OH. This is the structure of your H2S2O8. Now, my dear students, have a look exactly what it means. I mean, how do we get the oxidation states? If you look at this particular sulfur atom and this particular sulfur atom. First of all, there is S double bond O. Oxygen is more electronegative, so -2 and +2. Due to this double bond, it will be -2, this will be +2. Single bond, -1, +1. Single bond, -1, +1. What about the total charge on sulfur here? It will be +6. Similarly, total charge on sulfur here will be +6. So average oxidation state of sulfur in H2S2O8. First sulfur is showing +6. Second sulfur is also showing +6. There are two sulfur atoms. The net charge is coming out to be +6. So +6 is the average oxidation state of sulfur over here. If I ask you, is there any peroxide linkage? Yes, there is oxygen, single bond oxygen. Number of peroxide linkages is equal to 1. Number of oxygen atoms with -1 oxidation state is going to be 1 into 2. That comes out to be 2. So this was your H2S2O8, which you call as Marshall's acid. The fifth one, important one, Na2S4O6. 2 times from this particular compound, question has been asked in your JEE. Okay? Yeah? Sir, in oleum there is no, what are you saying? Sir, in oleum there is no number of peroxide linkage. Check it out. In oleum, where is oleum? This oleum. There is no oxygen single bond oxygen linkage. There is no O single bond O. Okay, Na2S4O6. First of all, do remember its structure. It's like this. This is the structure of your Na2S4O6. Okay. Now, dear students, look at one thing. When you talk about this particular sulfur atom, it's S double bond O, right? So this will show -2. This will show +2. Due to this double bond, again -2, +2. Due to this single bond, -1, +1. Now, due to this bond, nothing is going to happen because on both the sides, you've got sulfur. So what is the charge present on this particular sulfur? It's +5. What is the charge present on this sulfur? 0. Charge present on this sulfur? 0. Charge present on this sulfur? It will be +5. Perfect. So the correct set of charge on sulfur, the correct set of oxidation states of sulfur from left to right is +5, 0, 0, +5. Number 1. Number 2, calculate the average oxidation state of sulfur in case of your Na2S4O6. See, the first sulfur is showing +5 oxidation state, second sulfur 0, third sulfur 0, fourth sulfur +5, divided by total 4 sulfur atoms. So it will come out to be +2.5. So +2.5 is basically the average oxidation state of sulfur in case of your Na2S4O6. Right? Perfect. Perfect, guys. Is it clear till here? Quickly in the chats. Sudarsanam, I'm talking about those oxygen atoms which have got -1 oxygen state. They're showing peroxide linkage. See, you must be confused over here. This -1 is not the oxidation state of oxygen here. Right? Don't get confused. This charge is due to this particular bond. There is one more bond as well. Right? Due to this bond, it will have -1. This will have +1. So the oxidation state of oxygen right here will be -2. Right? Similarly here, sulfur oxygen, right? Oxygen is more electronegative. So this bond will be towards oxygen -1. This bond will be towards oxygen, again -1. So -2 here also. Perfect. You have to consider all the bonds if you want to check the oxidation state of all the elements. I hope I'm clear. There is no method to draw these structures. You have to remember them by practicing them, right? So this was your Na2S4O6. This was our fifth. Was it fifth or sixth? Fifth. Now sixth one. Sixth one. K3CrO8. K3CrO8. Look at its structure. This is Cr, oxygen, oxygen single bond, oxygen, oxygen, oxygen. This is one more. This is one more. This is one more. Now let me calculate the oxidation state of all the elements so that it becomes properly clear to you. I won't be calculating just the oxidation state of chromium. I'll be calculating the oxidation state of all the atoms. See. First of all, this single bond between chromium and oxygen, it will show -1, it will show +1. This single bond, -1, +1. This single bond, nothing will happen. Peroxide, right? This particular single bond, -1, +1. This particular single bond, -1, +1. This particular single bond, -1, +1. Peroxide, nothing will happen. Peroxide, nothing will happen. Peroxide, nothing will happen. Oxygen, potassium, -1, +1. -1, +1. -1, +1. Did I consider all the bonds? Yes, I considered all the bonds. Now you can easily check the oxidation state of each atom. So chromium will have the net charge of 1, 2, 3, 4, 5, +5. So +5 is the oxidation state of chromium over here. If I ask you how many peroxide linkages are here, peroxide linkages, 1, 2, 3, 4, 4 peroxide linkages. How many oxygen atoms are there with the oxidation state -1? There are 8 oxygen atoms with the oxidation state -1 over here. Yeah? Perfect. So this was your K3CrO8. Apart from that, look at the other structures as well. Other structures. Have a look. There is something called as H3PO2, H3PO3, H3PO4, H3PO5. Let's have a look on these structures as well. Okay. So first of all, everywhere I'm going to draw P double bond O. Everywhere I am going to draw P double bond O. Everywhere. P double bond O. This is P double bond O. Correct? Now, this is H3PO2. I have used one oxygen. There is one oxygen that's pending. So that is oxygen attached with hydrogen. So there were 3 hydrogens. I have used one. So 2 hydrogens directly attached with phosphorus. Over here, have a look. This is O. This is H. Perfect. This is O. This is H. And this H is directly attached with phosphorus. H3PO3. Now H3PO4. Oxygen with hydrogen. Oxygen with hydrogen. Oxygen with hydrogen as well. This is H3PO4. H3PO5. Oxygen with hydrogen. Oxygen with hydrogen. This is oxygen. This is oxygen. This is hydrogen. This is your H3PO5. These are the structures of these acids of phosphorus as well. You have to remember these structures because when we discuss the equivalent mass concept, there I'll be using these structures. So you have to remember them. Okay. Now, dear students, let me just show you one thing. This is P double bond O over here. Oxygen is more electronegative, so -2. This will show +2. Correct? Due to this single bond, oxygen -1, phosphorus +1. Due to this single bond, oxygen -1, hydrogen +1. Due to this single bond, phosphorus and hydrogen. Phosphorus is group 15. This is phosphorus is group 15 element, right? So more electronegative. So it will attract the bonded pair towards itself. So over here, I must say phosphorus will show -1 and hydrogen +1. Similarly, -1, +1. Check the net charge present on phosphorus. +2, +3. +3 -2 comes out to be +1. So +1 is the oxidation state of phosphorus here, right? Similarly, when you talk about this one, the oxidation state of phosphorus will be +3. The oxidation state of phosphorus will be +5. The oxidation state of phosphorus will be +5. Right? Perfect. It will be +5. If I ask you, in case of H3PO5, do you see any peroxide linkage? Yes, there's one peroxide linkage. So number of peroxide linkages here is 1. So how many oxygen atoms are there with -1 oxidation state? 2 oxygen atoms will be there with -1 oxidation state. I hope I'm perfectly clear for this. Okay. At the same time, do remember, if I particularly talk about phosphorus, phosphorus belongs to group 15. All the group 15 elements, they have got 5 valence electrons. Right? All the group 15 elements, they have got 5 valence electrons. So they can lose those 5 valence electrons, I can say, and they can show +5 oxidation state. So can I say Phosphorus, it has got 5 valence electrons. So it can lose all of them, for example. Perfect. And when it loses all of them, when those 5 electrons go far from phosphorus, phosphorus will show +5 oxidation state. Now you tell me, can phosphorus show +6? No, it can show +5, maximum +5 oxidation state only, right? Phosphorus can show maximum. This is the maximum oxidation state of phosphorus. For example, I've got carbon. It has got 4 valence electrons. It can lose all the 4. So its maximum oxidation state will be equal to +4 only. This is the maximum oxidation state of carbon. I hope you're getting what I'm trying to say. Why I'm telling you the maximum oxidation state concept over here? Because afterwards, after like 1 hour, you'll get to know something interesting, right? There are some set of questions which are asked from these things as well, right? Perfect. I hope all this is clear. So this was your H3PO2. 7th, this is 8th structure, this is 9th one, and this is 10th. Now, are there a few more structures? Yes, there are a few more structures. 11th one. What is that? That is C3O2. 12th one. That is Br3O8. 13th. BASCN whole twice. BASCN whole twice. 14th. CaOCl2. CaOCl2. Yeah, perfect. Now let's have a look on these structures. C3O8. This is, sorry, C3O2. This is your C3O2. Perfect. Br3O8. This is Br. This is Br. This is one more Br, right? Double bond, double bond, double bond here. Similarly, 3 double bonds on this side. 2 double bonds here. BASCN whole twice. This is BA, this is S, this is C, this is triple bond N. This is S, this is C, this is triple bond N. This is BASCN whole twice. CaOCl2, which is what you call as bleaching powder. Bleaching powder. This is Ca, this is O, this is Cl, and one Cl is directly attached with chlorine, with calcium. So these are some other structures as well, which you have to remember, my dear students. Okay. Now, one thing, I'll take one of the examples. See. For example, you have got C3O2. This is carbon double bond oxygen. Oxygen will show -2, due to which carbon will show +2. There is a double bond here, but on both the sides you have got carbon, nothing will happen. Both the sides carbon, nothing will happen. Oxygen, -2 and +2. Perfect. This oxygen is having 0 oxidation state. Now, if I ask you the average oxidation state of carbon over here, the first carbon is showing +2, second is showing 0, third is showing +2. There are 3 carbon atoms. So average oxidation state of carbon came out to be +4/3, right? +4/3. Now, similarly, look at this particular structure, right? So this will show, I'm showing the final one now, okay? This is +6, this is 0. Sorry, this is not 0. This is +4 because there are 2 double bonds, and this is +6 as well. So average oxidation state of bromine will be how much? +6, +10, +16. So +16 divided by 3 is the average oxidation state of bromine, right? Similarly, my dear students, you can talk about the other compounds as well. You can calculate the oxidation state of each element over here. No need to worry. If you know the structure, that's all. For example, you have got carbon triple bond nitrogen. Which one is more electronegative? Nitrogen. So it will show -3. Carbon will show +3. Single bond. Carbon and sulfur. Sulfur is more electronegative. -1, +1. Barium and sulfur. Sulfur is more electronegative. -1, +1. Sulfur more electronegative. -1, +1. Sulfur more electronegative. -1, +1. Nitrogen more electronegative. -3, +3. So check the oxidation state of all the atoms over here. Oxidation state of this nitrogen is -3. Oxidation state of this carbon is +4. Oxidation state of this particular sulfur is -2. Oxidation state of this barium, it's +2, right? And so on. I hope it is super clear to you. Yeah? Perfectly done. Now, similarly, look at this bleaching powder. This is calcium and chlorine. Chlorine -1, calcium +1. Single bond. This is -1, this is +1. Single bond. This is -1, this is +1. So calcium here is in +2 oxidation state. This particular chlorine is in -1 oxidation state. This particular chlorine is in +1 oxidation state, and this oxygen is in -2 oxidation state. If I ask you, what is the average oxidation state of chlorine in bleaching powder? You'll say one of the chlorine has got +1, another chlorine has got -1. There are 2 chlorine atoms. So average oxidation state of chlorine in bleaching powder, it comes out to be 0. So my dear students, these were some very, very, very important structures which you have to remember from now onwards, right? Is everything clear till here? Ramesh, you can check it, right? AClO3, chlorine, it will be having +5 oxidation state. Quickly, people, all clear? My dear students, quickly let me know in the chats if every single thing is clear to you. Quickly. So things about oxidation state, rules to calculate oxidation state and structures, it's done and dusted, right? Now people, let's try to have a look on few more things. So all these structures I've shown you, you're going to get it in the form of PDF in the Telegram afterwards, right? All these things we are done with. Okay. Perfect. Now people, since we got to know what oxidation state is all about, what are the rules by means of which we can calculate the oxidation state, and at the same time, my dear students, at the same time, I told you the structures which are really important when it comes to the oxidation state, right? Now, after this, I'll let you know how to define exactly the term oxidation and reduction. Okay? What is oxidation all about? See, there are a lot of definitions as far as the term oxidation is concerned. A lot of definitions related to oxidation. You need not to remember all the definitions. Just remember one. Oxidation, how do we define it? Oxidation means loss of electrons. Oxidation means loss of electrons. Whenever an element loses electrons, whenever an atom loses electrons, we say that atom undergoes oxidation. Simple. Loss of electrons is oxidation. That's it. Right? Similarly, if you ask me about reduction, reduction simply means gain of electrons. Reduction simply means gain of electrons. Okay? Whenever the atom gains some electrons, we say that atom undergoes reduction. Number one. One is loss of electron, that's oxidation. One is gain of electron, that is reduction. One more thing. How do we identify whether the element undergoes oxidation or reduction? There is a simple rule for that. Increase in the oxidation state of the element. Whenever you see increase in the oxidation state of the element, that means that element is undergoing oxidation. Whenever you see decrease in the oxidation state of the element, whenever you see decrease in the oxidation state of the element, we'll say that element undergoes reduction. For example, let me give you certain examples so that it will be properly clear to you. For example, I'm writing a reaction. Mg gives Mg di positive plus 2 electrons. This is one reaction, for example. Understand carefully. My dear students, if I ask you, is there any charge present on magnesium here? No. Is there any charge present on this magnesium? Yes, plus 2. So initial oxidation state of magnesium was 0 and the final oxidation state of magnesium is plus 2. What does that mean? Does that mean magnesium is undergoing increase in the oxidation state? Right? That element which undergoes increase in the oxidation state, we say that element undergoes oxidation. So magnesium is undergoing oxidation over here. Magnesium is showing increase in the oxidation state, so it's undergoing oxidation. And what does oxidation mean? Loss of electrons. That means magnesium is losing electrons. As you can see, it's losing 2 electrons. As simple as that. As simple as that. For example, I have got Cl2 plus 2 electrons. It is getting converted into Cl negative, 2 times Cl negative, something like this. Okay, I wrote one reaction. Dear students, do you see any charge on chlorine here? No, there is no charge present on chlorine. Do you see any charge on chlorine here? Absolutely, it's -1. Absolutely, it's -1. So 0 to -1. 0 to -1. Does it mean increase in the oxidation state or decrease in the oxidation state? Right? Does it mean increase or decrease? It means decrease in the oxidation state. Chlorine is undergoing decrease in the oxidation state. And do remember, decrease in the oxidation state is something which we call as reduction. And any species which undergoes reduction, that actually means it involves gain of electrons. Yeah? Perfect. So short mein, increase in the oxidation state means oxidation. Decrease in the oxidation state means reduction. Oxidation means loss of electrons. Reduction means gain of electrons. As simple as that. No need to remember anything new. Okay? Now, my dear students, if you got to know what is oxidation and what is reduction, let's try to identify the oxidizing and reducing agents in the reactions. How do we identify oxidizing and reducing agents? What are oxidizing and reducing agents? Have a look. First of all, I'll let you know a simple thing by means of which you can check whether the reactant is oxidizing or reducing agent. How do we do it? Okay. First thing, what is the charge present on magnesium? 0. The charge present on oxygen? 0. The charge present on magnesium? +2. The charge present on oxygen? -2. Basically, I calculated the oxidation states of different elements. Now, dear students, tell me whether the oxidation state of magnesium is increasing or decreasing. 0 to +2. Increase in the oxidation state of magnesium. Increase in the oxidation state means oxidation. So magnesium over here is undergoing oxidation. Number 1. Number 2. Oxygen from 0 to -2. 0 to -2. Decrease in the oxidation state. And decrease in the oxidation state is something which we call as reduction. Decrease in the oxidation state is something which we call as reduction. That species which undergoes oxidation, that is something which we call as a reducing agent, or you can call it as a reductant as well. That species which undergoes oxidation, is something which you call as reducing agent, or you call it as the reductant as well. And that particular species which undergoes reduction, that's called as oxidizing agent, or you can call it as oxidant as well. Simple. Simple, right? The one which undergoes oxidation is the reducing agent. The one which undergoes reduction is the oxidizing agent. Perfect? Can I say something like this? Reducing agent is the one which reduces others, but itself undergoes oxidation. Reducing agent reduces others, and itself it undergoes oxidation. Oxidizing agent, it oxidizes others, but itself undergoes reduction. Do you agree with this? Do you agree with this? You must. Okay? Oxidizing agent. It oxidizes others, but itself undergoes a reduction. Reducing agent. It reduces others. But itself undergoes. It reduces others, but itself it undergoes oxidation. I hope I'm clear with both these terminologies. Right? Perfect. Now, people, one more thing. Look at the reaction and identify the oxidizing and reducing agent quickly. Look at the reaction and identify the oxidizing and reducing agent quickly. Quickly, guys. Quickly. Quickly, everyone. See, first thing, if you want to calculate the oxidation state of this iron, it will be plus 2, right? X minus 2 is equal to 0. Manganese, plus 7. Iron, plus 3. Manganese, plus 2, right? Manganese, plus 2. Now check. Iron is changing its oxidation state from plus 2 to plus 3. Plus 2 to plus 3 means increase in the oxidation state. Increase in the oxidation state means oxidation. So I must say this FeO, it undergoes oxidation. The one which undergoes oxidation is something which you call as the reducing agent. Point number 1. Point number 2. Manganese is changing its oxidation state from plus 7 to plus 2. Decrease in the oxidation state. Decrease in the oxidation state is something which you call as a reduction. So I must say MnO4 negative, it undergoes reduction. The one which undergoes reduction, that has to be the oxidizing agent. Simple. Don't say Fe is the reducing agent. Don't say Fe is the reducing agent. Say it like this, FeO is the reducing agent. Don't say manganese is the oxidizing agent. No, you are going to say MnO4 negative is the oxidizing agent, right? Perfect. I hope I'm clear to you. Okay, what about this one? What about this one? What about this one? The oxidation state of zinc over here is 0. The oxidation state of copper right here is plus 2. The oxidation state of zinc over here is plus 2. The oxidation state of copper over here is 0. Perfect. Now, my dear students, zinc is showing increase in the oxidation state. Copper is showing decrease in the oxidation state. You know, increase in the oxidation state is something which we call as oxidation. So I would say zinc is undergoing oxidation, right? Decrease in the oxidation state is something which we call as a reduction. So I must say Cu di positive is undergoing reduction. The one which undergoes oxidation, that has to be the reducing agent. The one which undergoes reduction, that has to be the oxidizing agent. Perfect. Clear? So I hope you got to know how to identify the oxidizing and reducing agent. So first of all, how do we define the term equivalent mass? I'll be firstly writing its definition, then I'll make you understand what this equivalent mass exactly is all about. Okay? So let me write the definition. Equivalent mass is defined as that mass of the substance in grams which can combine or displace either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver or 80 grams of bromine. This is first of all the definition of the term equivalent mass. That mass of the substance in grams which can combine or displace either 1 gram of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver or 80 grams of bromine. Now the point is, what is meant by it? How can we exactly understand it? So for your understanding, let me make it a little more simpler. Let me make it a bit clear to you. See guys, for example, I'm writing one balanced chemical equation. That is N2 plus 3 times H2, it gives NH3. It gives 2 times NH3. This is, for example, one balanced chemical equation. Okay? For example, I'm asking you to calculate the equivalent mass of nitrogen. I'm asking you to calculate the equivalent mass of nitrogen. First of all, have a look. Can I say nitrogen in this reaction is combining with hydrogen? Yes, it does. Nitrogen is combining with hydrogen. Perfect. And I'm asking you to calculate equivalent mass of nitrogen. That means I need to calculate that mass of nitrogen. I need to calculate that mass of nitrogen in grams, which has combined with 1 gram of hydrogen. That mass of nitrogen which has combined with 1 gram of hydrogen. That's something which I'll be calling as equivalent mass of nitrogen. What it means exactly? Have a look. See guys. First of all, if I ask you, what is the mass of 1 mole of N2? What is the mass of 1 mole of N2? Mass of 1 mole of N2 means molar mass of N2, right? And molar mass of N2, all of you are familiar with, it's 28 grams, right? Similarly, what is the mass of 1 mole of H2? The mass of 1 mole of H2, which you call as molar mass of H2, that is 2 grams. So if the mass of 1 mole of H2 is 2 grams, then the mass of 3 moles of H2 has to be 6 grams. Correct? Now people, can I say 6 grams of hydrogen, 6 grams of hydrogen has combined with 28 grams of nitrogen? Right? Can I say something like this? From the stoichiometry of the reaction, I got to know 6 grams of hydrogen has combined with 28 grams of nitrogen. If I use the unitary method, can I say 1 gram of hydrogen has combined with 28 divided by 6, that is 14 by 3 grams of nitrogen? Perfect. Now, if I ask you what it exactly means, what did we calculate? What is this term? What is this term? If I ask you what is this term, you will say 14 by 3 grams. It is basically that mass of nitrogen. It is basically that mass of nitrogen which has combined with 1 gram of hydrogen. And that mass of substance which combines with 1 gram of hydrogen, that's something which I call as equivalent mass of substance. So can I say I got to know the equivalent mass of nitrogen over here, which came out to be 14 by 3 grams? Right? So this is the mass of nitrogen which has combined with 1 gram of hydrogen, and that mass of substance which combines with 1 gram of hydrogen, that's something which you call as equivalent mass of the substance. Perfect. So quickly in the chats, let me know if all these things are clear to you. So I got to know the equivalent mass of nitrogen right now. Yeah. My dear students, let me take one more example so that it becomes properly clear to you. For example, I'm writing a reaction. The reaction is like this: Mg plus O2. It gives MgO. Let me try to balance it. This should be 2 times. Even this should be 2 times. Now it's a balanced chemical equation. For example, I'm asking you to calculate the equivalent mass of magnesium. I'm asking you to calculate the equivalent mass of magnesium. First of all, have a look. Magnesium is reacting with oxygen. Magnesium is reacting with oxygen. And I'm asking you to calculate equivalent mass of magnesium. That means I'm asking you to calculate that mass of magnesium which has combined with 8 grams of oxygen. I'm asking you to calculate that mass of magnesium which has combined with 8 grams of oxygen. Now, dear students, use the stoichiometry again. What is the mass of 2 moles of magnesium? It has to be 48 grams, right? What is the mass of 1 mole of oxygen? It has to be 32 grams. As simple as that, right? Can I say, from the stoichiometry of the reaction, can I say 32 grams of oxygen has combined with 48 grams of magnesium? Absolutely, I can say that. If 32 grams of oxygen has combined with 48 grams of magnesium, can I say 1 gram of oxygen? Can I say 1 gram of oxygen? 1 gram of oxygen has combined with 48 divided by 32 grams of magnesium? Absolutely. Can I say 8 grams of oxygen? 8 grams of oxygen has combined with 48 divided by 32 multiplied by 8. The value comes out to be 8184. So it comes out to be 12 grams. Now you tell me in the chats what this 12 grams of magnesium means over here. What it means exactly. Can you let me know? My dear students, this is the mass of magnesium. This is the mass of magnesium which has combined with 8 grams of oxygen, and that mass of substance which either combines with 1 gram of hydrogen or 8 grams of oxygen, that's something which I call as equivalent mass of the substance. So equivalent mass of magnesium over here came out to be 12 grams. I hope it's super clear to you, right? Let me know once in the chats if it is clear to you, quickly. Quickly, my dear students. Quickly, everyone. Everyone quickly. Perfect? Absolutely. Now, similarly, for example, if I have the reaction like this, Al plus Cl2, let's say it gives AlCl3. This is the reaction. I'm asking you to calculate the equivalent mass of aluminium. I'm asking you to calculate equivalent mass of aluminium. What does that mean? That means you have to calculate that mass of aluminium which has combined or displaced 35.5 grams of chlorine. As simple as that. So this is how you actually check the equivalent mass of different substances. This is actually how you check the equivalent mass of different substances. Okay? For example, I'm giving you a question like this. A simple question. I'm asking you, calculate the equivalent mass of sulfur in for example, S2Cl2. Right? For example, there's one simple question. Calculate the equivalent mass of sulfur in S2Cl2. Can't you do it? Can't you do it? My dear students, first of all, see the formation of S2Cl2. S2Cl2 has to get formed, correct? So on this side, you have got 2 sulfur atoms. So 2 sulfur atoms would have reacted with 2 chlorine atoms. They would have formed S2Cl2. Absolutely. Now people, if I ask you something like this, to calculate the equivalent mass of sulfur, right? Equivalent mass of sulfur. Now people, understand properly. What is the mass of 2 moles of sulfur? Mass of 1 mole of sulfur is something which you call as molar mass of sulfur. That is 32 grams. So mass of 2 moles of sulfur has to be 64 grams. And mass of 2 moles of chlorine has to be 71 grams. So can I say 71 grams of chlorine? 71 grams of chlorine has combined with 64 grams of sulfur? Absolutely. Right? So can I say 1 gram of chlorine has combined with 64 divided by 71 grams of sulfur? Absolutely. So can I say 35.5 grams of chlorine? 35.5 grams of chlorine has combined with 64 divided by 71 multiplied by 35.5. The value comes out to be 32 grams of sulfur. So just check, what did I calculate? Check it out. What did I calculate? Can I say I calculated that mass of sulfur which has combined with 35.5 grams of chlorine, and that mass of substance which either combines with 1 gram of hydrogen or 8 grams of sulfur or 35.5 grams of chlorine? That's something which you call as equivalent mass of that substance. So I got to know the equivalent mass of sulfur in S2Cl2 is basically 32 grams. Is this clear to everyone? Is this clear to everyone, people? Everyone. For example, I'm asking you to calculate the equivalent mass of sulfur in SO3. In SO3. Can you do that? The equivalent mass of sulfur in SO3. Absolutely, you should be doing that. So first of all, I'm making SO3. SO3 would have formed when 1 sulfur atom would have combined with 3 oxygen atoms. Then SO3 would have formed, right? Perfect. You can take oxygen in O2 format as well. Then you have to balance the reaction. That's headache. I'm not going to do that. I'm trying to make it simpler for you. Okay. Now people, understand. Mass of 1 mole of sulfur is 32 grams. Mass of 3 moles of oxygen is 48 grams. Correct? So can I say 48 grams of oxygen as combined with 32 grams of sulfur? Absolutely. So 1 gram of oxygen has combined with 32 divided by 48 grams of sulfur? Absolutely. So can I say 8 grams of oxygen has combined with 32 divided by 48 multiplied by 8? And this is going to be grams of sulfur. Perfect. 8 1, 8 6. So 32 by 6 means 16 divided by 3. 16 divided by 3 grams of sulfur. So what did I calculate? What is this term? What is this particular term? Can I say it is basically that mass of sulfur which has combined with 8 grams of oxygen, and that mass of substance which combines with 8 grams of oxygen, that's also what we call as equivalent mass. I hope this is clear. Right? Now, dear students, I am going to give you one direct result which you are going to remember from now onwards to calculate equivalent mass of any substance. Okay? To calculate equivalent mass of any substance. And that formula is, do remember it from now onwards. That formula is equivalent mass of the substance is always equal to molar mass of the substance divided by n factor, or what we call as valency factor of the substance. This is one very, very, very important result. This is one very, very, very important result. Whenever a question comes related to equivalent mass, you'll be always using this formula. Equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the substance. Now the point is, see, molar mass of each and every substance we know. Now the point is, how can we calculate n factor of different substances? So this is our actual topic right now. How do we calculate the n factor of different substances? So you mark the heading as n factor calculation. You mark the heading as n factor calculation. This is something very, very, very important, which will be almost used everywhere in your physical chemistry. N factor calculation. And this is one big topic basically. Okay? So n factor calculation. How do we calculate n factors of different substances? See guys. First thing, that is n factor of an element. N factor of an element. Do remember, n factor of an element is always equal to the valency of the element. N factor of the element is always equal to the valency of the element. For example, let's have an example first of all. For example, I'm taking nitrogen into consideration. Let's say I've got oxygen, right? Let's say I've got sodium. These are three elements which I took over. If I ask you, what is the valency of nitrogen? You will say valency of nitrogen is 3. I'm not talking about the valence electrons. I'm talking about the valency. Valency of nitrogen is 3. Valency of oxygen is 2. Valency of sodium is 1. Right? And whatever is the valency of the element, that's something which you will be calling as n factor of the element. Right? So can I say I got n factors of these elements? Well, if you got the n factor of the element, can't you calculate equivalent masses? So equivalent mass of nitrogen will be equal to molar mass of nitrogen, which is 14 grams, divided by n factor of nitrogen, which is 3. So 14 by 3 grams is the equivalent mass of nitrogen here. Perfect. Similarly, equivalent mass of oxygen has to be equal to molar mass of oxygen, 16 grams, divided by n factor 2. The value has to be 8 grams. Perfect. Similarly, if I ask you equivalent mass of sodium, which has to be equal to molar mass of sodium, which is 23 grams, divided by n factor, the value comes out to be 23 grams. Right? So whenever we are supposed to calculate equivalent mass of the element, we should know the valency of the element. And whatever is the valency of the element, that's something which you will be calling as n factor of the element. And once you get the n factor, divide the molar masses by their respect to n factors, you'll be easily getting the equivalent masses of different elements. So this was n factor first, which is n factor of an element. Number 1. Number 2. N factor of a salt. How do we calculate the n factor of the salt? Let me tell you, n factor of the salt is always equal to the LCM of charge on cation and anion. We have to take the LCM of charge present on cation and anion. Now, my dear students, let's have a look. How do we calculate it? For example, I'm taking certain salts. Let's say I'm taking NaCl. Perfect. Let's say I have got Al2SO4 whole thrice. These are two salts which I've taken, right? Now, first of all, whenever we write a salt, for example, NaCl, this is the representation of NaCl. First one will be always your cation, second one will be always your anion. First one will be always your cation, second one will be always your anion. Perfect. Now, dear students, it's basically Na1Cl1. So this particular one will be the charge of sodium. This particular one will be the charge of chlorine. This 3 will be the charge of aluminium. This 2 will be the charge of sulfate, right? Something which you have discussed in class 9th, crisscross. Crisscross, that's it, right? Now, people, just take the LCM of. LCM of what? Charge on cation, that's 1. Charge on anion, that's 1. So LCM of 1 and 1 came out to be 1 only. Now, if I ask you, what about the LCM of charge present on cation and anion here? Charge present on cation is 3 and charge present on anion is 2. So the value has to be 6, right? And as I told you, LCM of charge present on cation and anion, that gives me the N factor of the salt. So basically, 1 is the N factor of NaCl and 6 is the N factor of aluminum sulfate. Perfect. So if you got the N factors, you can easily calculate their equivalent masses. So I must say equivalent mass of NaCl. I must say equivalent mass of NaCl will be equal to molar mass of NaCl, right, divided by its N factor. Similarly, equivalent mass of aluminum sulfate will be equal to its molar mass divided by its N factor. That's all, right? So first was N factor of elements. That's always equal to the valency. N factor of salt, it is always equal to the LCM of charge present on cation and anion. The third thing, my dear students. Third thing is N factor of an acid. This is important. N factor of an acid. N factor of an acid is always equal to the basicity of the acid. It is always equal to the basicity of the acid. Now you must be thinking, what is basicity? How do we define it? Simple, it's defined as number of H positives and acid donates. Number 1, you can define it in one more way. Number of OH negatives and acid accepts, right? This is one more way of defining it. Now try to understand. This is something which is very, very, very important. For example, I'm taking certain acids, HCl, H2SO4, HNO3, H3PO4. These are some acids which I've taken. Okay. Now you tell me, if I put this HCl into water, how many H positives it's going to give me? It's going to donate 1 H positive. When you put this H2SO4 into water, it's going to donate 2 H positives. This is going to donate 1 H positive. This is going to donate 3 H positives. Correct? The number of H positives an acid donates, it defines the basicity of the acid. And whatever is the basicity of the acid, that's something which you'll be calling as N factor of the acid. So I would say N factor of HCl over here is 1. N factor of H2SO4 over here is 2. N factor of HNO3 over here is 1. And N factor of H3PO4 over here is 3. Perfect. So dear students, if you got the N factors of these acids, can't you calculate their equivalent weights? So can I say equivalent mass of HCl will be equal to molar mass of HCl divided by 1. Molar mass of H2SO4 divided by 2. Molar mass of HNO3 divided by 1. Molar mass of H3PO4 divided by 3. Isn't it simple? People? Right? Now, let me change some things about acids. Have a look. For example, I'm using H3PO2, right? Then I'm taking H3PO3. Then I'm taking H3PO4. And then I'm taking H3PO5. Perfect. What do you think should be the N factor of this H3PO2? Normally, you'll think that there are 3 hydrogens. When you'll put into water, it will donate 3 H positives. This will also donate 3 H positives. This also 3. This also 3. So N factor of all these substances should be 3 as per you, right? But take a note of one statement. An acid donates only that H positive. An acid donates only that H positive which is attached. An acid donates only that H positive which is attached to more electronegative element. To more electronegative element like chlorine, oxygen, or nitrogen. An acid will donate only that H positive which is attached to more electronegative element like fluorine, oxygen, nitrogen. Now, if you remember the structure of H3PO2, which I gave you long back, this is the structure of your H3PO2, correct? Structure of H3PO3. Structure of H3PO3. This is the structure of your H3PO3. Similarly, structure of H3PO4. Structure of H3PO4. This is the structure of H3PO4. Structure of H3PO5. This is the structure of H3PO5. Now, my dear students, if you look at the first acid, how many hydrogens are connected, are attached to more electronegative element like oxygen? There is only one hydrogen. Over here, there are two hydrogens which are attached to more electronegative element. There are three hydrogens which are attached to more electronegative element. Three hydrogens attached to more electronegative element. And an acid, it donates only that H positive which is connected to more electronegative element like fluorine, oxygen, or nitrogen. Yeah. So, my dear students, this acid is going to donate this particular H positive. So, it's going to donate only one H positive. If it is donating only one H positive, that means its basis T is 1. Its N factor is 1. It is donating 2. So, its N factor has to be 2. Its N factor has to be 3. Similarly, its N factor has to be 3. So, if you got to know the N factors of these acids, can't you calculate their equivalent masses? Yeah. Molar mass of H3PO2 divided by its N factor. Molar mass divided by N factor. Molar mass divided by N factor. That's all. Right? I hope it's clear. Now, in case of acids, I told you an acid donates only that H positive, which is attached to more electronegative element. But my dear students, if you talk about boric acid, boric acid, what is the formula through which we represent boric acid? It is H3BO3. Or sometimes in the questions, they might confuse you. With the formula. They'll make the formula of boric acid like this, BOH whole thrice, so that it looks like a base to you. But it's actually H3BO3 only, right? Boric acid is a special case. Boric acid is basically, it's a special case, right? Why is it special? Let's have a look, understand. My dear students, if you look at the structure of boric acid, right? This is the structure of your boric acid. H3BO3. Perfect. This is the structure of your boric acid. Now, when you will introduce this boric acid in water, what will happen? This is your water. For example, you are introducing this boric acid in water. Now, what is going to happen here? Understand. My dear students, if I ask you whether this boron over here, whether it is electron deficient center or electron rich center, check its octet. It's incomplete. 6 electrons in its octet. So it's incomplete, right? It's incomplete. Perfect. The octet is incomplete. It has only 6 electrons in its valence shell. But how many it should have? It should have 8. So now you are introducing this boric acid into water. This is electron deficient center. If it gets electrons from somewhere, it's absolutely going to accept it. If it is going to get electrons from somewhere, it is going to accept it because it is electron deficient. Now, since you have introduced in water on oxygen, you have got 2 lone pairs. Now, what's going to happen? What oxygen will do? Oxygen will donate one of the lone pair towards boron in the form of a coordinate bond. The donor atom gets the positive charge. The acceptor atom gets the negative charge. Now, dear students, I'm sure that you would have studied something in organic. What is that? positive charge on an electronegative element makes it unstable, right? Generally, positive charge on an electronegative element makes it unstable. Yeah, right? Positive charge on an electronegative element makes it unstable. Or you can say positive charge on an electronegative element makes it more electronegative. So what is going to happen? Since oxygen is carrying the positive charge now, so it's comparatively unstable. So it will try to attain back its stability. So what this oxygen will do, it will break one of the OH bond towards itself. It will break one of the OH bond towards itself and make sure one of the hydrogen leaves as H positive. One of the hydrogen leaves as H positive. So what will be getting? This was B. This is OH, the one which already have. This is one more OH. It already had this. It already had this. Now there is a bond over here. There is a bond over here. Between what? Between boron and oxygen, right? And oxygen is now attached to only one hydrogen. Initially, there was a positive charge on oxygen. Now the bond has been broken down towards oxygen. So positive charge is nullified. This boron is having negative charge. And this particular hydrogen has been lost in the form of H positive. So this is something which happened here. This is something which happened here. Now, first of all, this boron, it accepted a pair of electrons. Any species which accepts a pair of electrons, that's something which we call as Lewis acid. So this is the example of a weak Lewis acid. It is the example of a weak Lewis acid, right? If I ask you how many H positives it donated one H positive. But was this H positive its own, or it was the hydrogen of water? It was basically the hydrogen of water which it donated, right? But if I ask you how many OH negatives it accepted, how many OH negatives it accepted? Here it has 3 OH. Now it has 4 OH. So it has accepted 1 OH negative. It has accepted 1 OH negative. Boric acid has accepted 1 OH negative. And the number of OH negatives an acid accepts, that decides, that defines the base state. That defines the base state. So let me quickly summarize it. This was your boric acid, H3BO3. When I introduced it into water, what happened? What happened? It got converted like this. BOH4 negative plus H positive. Perfect. So this boric acid accepted 1 OH negative. And the number of OH negatives accepted by an acid, that defines its base state. And whatever is the base state, that is the N factor. So N factor of boric acid over here is 1. It's not 3. Quickly in the chats if it is clear. Quickly in the chats if it is clear. Quickly, guys. One more thing I would want to share with you related to the acids. Take a note of this statement as well. Do remember an acid, or let me write it like this. Equivalent mass of an acid. Equivalent mass of an acid changes on changing. Equivalent mass of an acid changes on changing the type of the reaction. On changing the type of the reaction. This is again one important statement. And why is it important? Let's get to know. Dear students, I'm writing 2 reactions here. One is H2SO4 plus NaOH. NaOH. For example, it gives NaHSO4 plus water. It is one balanced chemical equation. Now I'm writing one more similar equation. H2SO4 plus 2 times NaOH. Plus 2 times NaOH. What does it give me? For example, it will give me Na2SO4. And with this, I'm writing 2 times water. These are 2 reactions which I wrote over here. Now the point is, why did I write these reactions? There is something which you have to understand from here. Right? There is something which you have to understand over here. Understand properly. See guys, H2SO4, H2SO4. I want to calculate equivalent mass of H2SO4 in both the reactions. I want to see whether equivalent mass of H2SO4 in both the reactions will be same or different. I want to see that. And how exactly? See, first of all, one common thing. You know, when one H positive reacts with one OH negative, it leads to the formation of one water molecule. You must be knowing this, right? You can say it like this also. When 1 mole of H positive reacts with 1 mole of OH negative, it leads to the formation of 1 mole of water. Similarly, when 2 moles of H positive reacts with 2 moles of OH negative, it leads to the formation of 2 moles of water. Correct? Yes. Now people, in the first reaction, how many moles of water are being formed? 1 mole of water is being formed. 1 mole of water is being formed. How exactly? That means this H2SO4 would have donated 1 H positive and this would have donated 1 OH negative. They would have reacted. They will have led to the formation of 1 mole of water. Right? Similarly, in the second reaction, 2 moles of water are being formed. So in order to produce 2 moles of water, I must say this H2SO4 would have donated 2 H positives. This would have donated 2 OH negatives and they would have reacted and led to the formation of 2 water molecules over here. Now you tell me, how many H positive this acid is donating? 1 H positive. Number of H positives acid donates, that defines its basis state. That defines its N factor. So I would say N factor of H2SO4 in this particular reaction, that's 1. That's 1. Similarly, what is the N factor of H2SO4 in this reaction? N factor of H2SO4 in this reaction is 2. Right? So now you got to tell me whether H2SO4 has got same N factor in both the reactions? No. N factor is different. If the N factor of H2SO4 in these reactions is different, can I say equivalent masses of H2SO4 will be also different? Because equivalent mass is equal to molar mass divided by N factor. If N factor is coming out to be different, that means equivalent mass will come out to be different. So can I simply generalize a statement? The statement is simple like this. Equivalent mass of the substance. Equivalent mass of the substance. Is it a fixed quantity or a variable quantity? Equivalent mass of the substance is a variable quantity, which changes upon changing the type of the reaction. Equivalent mass of the substance, it is a variable quantity, unlike molar mass. Unlike molar mass. Molar mass of the substance, that's always fixed, but equivalent mass, that can change on changing the type of the reaction in which it participates. Quickly in the chats, if every single thing about the acids is clear. Quickly, my dear. Quickly. So let's talk about the third N factor. That is the N factor of bases. How do you calculate the N factor of bases? N factor of a base is always equal to. It is always equal to the acidity of the base. It is always equal to the acidity of the base. Now, how do you define the term acidity? How do you define the term acidity? It is defined as number of OH negatives a base donates. A base donates, or I can say number of H positives a base accepts. The number of H positives a base accepts. Now, what is meant by that? For example, I've got NaOH. I've got KOH, right? I've got BaOH whole twice. Perfect. Correct? Now, guys, one thing. When you'll put this NaOH into water, how many OH negatives it's going to give us? It's going to donate 1 OH negative. This one will donate 1 OH negative. This one will donate 2 OH negatives. The number of OH negatives a base donates, that defines its N factor. So I would say N factor of NaOH in this particular reaction, that's 1. N factor of KOH in this particular reaction, that's 1. N factor of BaOH whole twice in this particular reaction, that's 2. Well, if you've got to know the N factors of these bases, can't we calculate their equivalent masses? Molar mass divided by 1. Molar mass divided by 1. Molar mass divided by 2. That's all. That's all, right? Now, people, for example, I'm taking NH3, ammonia, which is a base. It's a base, right? NH3. Similarly, after NH3, what do? I'm taking NH2, CH2, CH2, NH2. Perfect. Now NH3 as well as this particular compound, I'm going to introduce them into water. I'm going to put them into water. I want to check the N factors of this NH3 and the other substance. Dear students, water has got H positives. Water has got H positives, correct? As well as OH negatives. First of all, this nitrogen over here, it has got a pair of electron, which you call as lone pair, right? Because nitrogen has got 5 valence electrons. Out of 5, it is utilizing 3. So 2 will be left as such in the form of a lone pair. Perfect. In case of water, there are already H positives, which are electron deficient, right? So can I say this nitrogen is going to accept H positive from it, from the water, and it will get converted into NH4 positive? Perfect. Absolutely. And when I introduce this particular substance into water, water already has H positives. This nitrogen has got 1 lone pair. Even this nitrogen has got 1 lone pair. So water already has got H positives. So I would say this lone pair is going to attack 1 H positive. This lone pair is going to attack 1 more H positive. So can I say this particular species, it is accepting 2 H positives? And the number of H positives a species accepts, the number of H positives a base accepts, that defines its N factor. So N factor of this substance over here is 2. And N factor of this substance over here was 1. If you got to know their N factors, you can easily calculate their equivalent weights. Correct? Yeah, I can say that. I can say that. Now, dear students, one more thing. One more thing. Take a note of this as well. When you talk about the base, equivalent mass of a base, equivalent mass of a base also changes on changing. Equivalent mass of the base also changes on changing the type of the reaction. The type of the reaction. What does that mean? Let's have a look. Again, for example, I'm going to write 2 reactions. Let's say this one reaction. Let's say it gives, right? This is, for example, one reaction. Similarly, I'm writing one more reaction. Okay. Both the reactions are balanced chemical equations. These are balanced chemical equations. Now, I'm asking you simply to calculate equivalent mass of this and equivalent mass of this. Okay. In order to calculate equivalent mass, what do I need? I need N factor. So basically, indirectly, I'm asking you to calculate N factor of zinc hydroxide. Indirectly, I'm asking you to calculate N factor of zinc hydroxide in both the reactions. Can we do that? Exactly, I can. See. First of all, in this particular reaction, 1 mole of water is being formed. In order to form 1 mole of water, can I say this would have donated 1 mole of H positive? This would have donated 1 mole of OH negative. 1 mole of OH negative. And they would have combined and led to the formation of 1 mole of water. Right? Similarly, in the second reaction, 2 moles of water are being formed. Does that mean this would have produced 2 moles of H positive? This would have produced 2 moles of OH negative. They would have reacted and led to the formation of water. Now, dear students, in the first reaction, how many OH negatives this particular species is donating? It is donating 1 OH negative. And number of OH negatives a base donates, that defines the acidity of the base, which is what you call as N factor. So N factor of ZnOH whole twice in the first reaction is 1. In the second reaction, the same species is donating 2 OH negatives. So its N factor in the second reaction is 2. Right? So N factor of ZnOH whole twice in both the reactions is different. That means equivalent masses of zinc hydroxide in both the reactions will be different. Correct? So again, I can generalize the statement that equivalent mass is a variable quantity. Equivalent mass is a variable quantity, unlike molar mass. unlike molar mass, right? Equivalent mass of the substance can change on changing the type of the reaction in which it participates. I hope it is super clear to you. So quickly in the chats, if all these things are clear. Quickly in the chats, if all these things are clear. Quickly, guys. Quickly, everyone in the chats, yes or no? Yeah, perfect. So I hope you got to know how to calculate equivalent mass of elements, equivalent mass of salts, equivalent mass of acids, equivalent mass of bases. I hope everything is clear till here. Now comes the actual stuff. You must be thinking all the time I'm telling you, now comes the actual stuff. Where is the actual stuff? Yeah. Okay. Now we are going to discuss equivalent weights, or basically we are going to discuss n factors of oxidizing and reducing agent. N factors of oxidizing and reducing. How do we calculate the n factors of oxidizing and reducing agents? First of all, if I ask you why do I need the n factors of oxidizing and reducing agents, you'll say in order to calculate equivalent masses of oxidizing and reducing agents. So basically now I'm going to show how do we calculate the equivalent masses of oxidizing and reducing agents. And in order to calculate the equivalent masses of oxidizing and reducing agents, what do we need? We need their n factors. So our topic is now n factor of oxidizing and reducing agents. This is the fourth part of the n factor. This is the fourth part of n factor. Part 1 was n factor of elements. Part 2 was n factor of salts. Then n factor of acids. Then n factor of bases. So this has to be the fifth part. This has to be the fifth part. Guys, have a look. N factor of oxidizing agent or reducing agent. N factor of oxidizing or reducing is always equal to number of moles of electrons, lost, gained, or exchanged by 1 mole of substance. By 1 mole of substance. Number of moles of electrons lost, gained, or exchanged by 1 mole of substance. Now you must be thinking, how will we get to know that how many moles of electrons are lost by a substance? How many moles of electrons are gained by a substance? Or how many moles of electrons are exchanged by a substance? You must be thinking about that as well, right? You must be thinking about that as well. So let's make it damn clear to you. See guys, just to make you understand, for example, I'm writing one general reaction, A plus B, it gives A positive plus B negative. A positive plus B negative. Yeah. Now, dear students, if I ask you, is there any charge on A over here? No. Its oxidation state is 0. Oxidation state 0. Oxidation state plus 1. Oxidation state minus 1. Correct? Well, have a look. Is the oxidation state of A increasing or decreasing? 0 to plus A. Oxidation state of A is increasing. If oxidation state of A is increasing, that means A is undergoing oxidation. A is undergoing oxidation. That means A is losing electrons. That means A is losing electrons. And that species which undergoes oxidation, that's what we call as reducing agent. So A is a reducing agent here. Talking about B, 0 to minus 1. 0 to minus 1. decrease in the oxidation state. 0 to -1, decrease in the oxidation state. Decrease in the oxidation state is something which you call as a reduction. So I would say B is undergoing reduction. Reduction means gain of electrons. So B is undergoing gain of electrons. And the one which undergoes reduction, that is the oxidizing agent. So first of all, you identified which is oxidizing agent and which is reducing agent. Now it is the time to calculate N factor of oxidizing agent. N factor of oxidizing, which is B. So N factor of B. N factor of B. How do you do it? Simple thing I'm going to tell you. First, write this mod, magnitude. Since I want to calculate N factor of B, correct? N factor of B is equal to, I will be calculating change in the oxidation state of B. I will be calculating change in the oxidation state of B. This is the initial oxidation state of B, and this is the final oxidation state of B. Calculate the change. Final oxidation state of B minus initial oxidation state of B. The value comes out to be 1. This one I'll be calling as N factor of B. This one I'll be calling as N factor of B. Now guys, what this 1 exactly signifies? Since this particular B, this B over here, it is an oxidizing agent. It is undergoing reduction. That means it's gaining electrons. So this 1 means that 1 mole of electron is gained by 1 mole of B. This is the meaning of the N factor here. This is the meaning of the N factor here. 1 is the N factor of B, and B is gaining electrons. So that means 1 mole of electron is being gained by 1 mole of B. Now, for example, I'm asking you to calculate N factor of A. N factor of A. Change in the oxidation state of A. Initial oxidation state of A, final oxidation state of A. Calculate the change. Final minus initial. Final minus initial. The value comes out to be 1. So this one is the N factor of A. Now this A over here, it undergoes oxidation. It involves loss of electrons. So what does this 1 signify over? It means that 1 mole of electron is lost by 1 mole of A. I hope it is super clear to you. Yeah? I hope it's clear to you. Now, my dear students, one more thing. For example, I'm modifying things. Let's say you have got a reaction in this format. A2 plus B2. Let's say it gives 2 times A positive plus 2 times B negative. This is the reaction, for example. Okay. First thing, if I ask you, what is the oxidation state of A over here? It's 0. Oxidation state of B over here, 0. Oxidation state of A over here, +1. Oxidation state of B over here, -1. Correct? This is something which you know now. Now, can I say A is undergoing increase in the oxidation state? B is undergoing decrease in the oxidation state. Correct? Increase in the oxidation state is something which we call as oxidation. So this A2 is undergoing oxidation. Oxidation means loss of electron. The one which undergoes oxidation, that has to be called as a reducing agent. Yeah? Similarly, talking about this B2, decrease in the oxidation state. Decrease in the oxidation state is something which you call as reduction. The one which undergoes reduction, that involves gain of electrons. The one which undergoes reduction, that has to be called as the oxidizing agent. So first of all, I identified the oxidizing and reducing agents. I identified. Now, let's calculate the N factor of this A2 over here. For example, N factor of A2. I'll be using the term mod. N factor of A2 is equal to change in the oxidation state of A2. Initial oxidation state, final oxidation state. So final minus initial. Final minus initial. The value comes out to be 1. But this 1 is not the N factor. This 1 is not the N factor. This 1 is the change in the oxidation state. This 1 is the change in the oxidation state of 1 atom of A. But over here, I have 2 atoms. So I'll be multiplying it with 2 over here. The value comes out to be 2. This 2 is the N factor of A2. This 2 is the N factor of A2. So do remember, the one whose N factor is to be calculated, you have to look at its subscript as well. You have to look at its subscript as well. And at the end, you have to multiply with that subscript. I hope I'm clear to all. Now, people, what does this 2 signify? Since this A2 undergoes oxidation, it involves loss of electrons. What does this 2 signify? It means 2 moles of electrons. 2 moles of electrons are lost by 1 mole of A2. 2 moles of electrons are lost by 1 mole of A2. Yeah? Now, similarly, if I ask you to calculate n factor of B2, how do you do it? Calculate the change in the oxidation state of B. This is initial, this is final. So final minus initial. Final minus initial. The value comes out B1. This one is the change in the oxidation state for 1 atom of B. But over here, do I have 1 atoms or 2 atoms? I have 2 atoms. Multiplied with 2. The value comes out B2. So this 2 is the n factor of B2. Now this particular B2, it undergoes reduction. It involves gain of electrons. So from this n factor, I got to know that 2 moles of electrons are gained. 2 moles of electrons are gained by 1 mole of B2. If this is clear to everyone, quickly let me know in the chats with the thumbs ups. Everyone quickly. Everyone quickly. So do remember, the one whose n factor is to be calculated, you have to look at the subscript of it. For example, this was 5 times. You have nothing to do with the stoichiometric coefficient here. You just have to look at the subscript, the smaller one, right? That's what you have to take care of. That's it. Enough. Perfect. Now, guys, let me tell you one more thing. When it comes to oxidizing agents, there are 2 very, very, very important oxidizing agents. One is your KMnO4, one is your K2Cr2O7. These are very, very, very important oxidizing agents, my dear students. KMnO4 and K2Cr2O7. Now, we'll be discussing few important things about KMnO4 and K2Cr2O7. So first of all, if I talk about KMnO4, some special things about KMnO4. My dear students, this particular KMnO4, which is basically a strong oxidizing agent, it shows different reactions in different mediums. This KMnO4, it shows different reactions in different mediums. When KMnO4 participates in the acidic medium, it gets converted into Mn di positive. When KMnO4 participates in acidic medium, it gets converted into Mn di positive, right? Mn di positive. When it participates in slightly basic, or I'll say slightly alkaline or neutral medium. When it participates in slightly alkaline or neutral medium, it gets converted into MnO2. And when the same KMnO4, when it participates in strongly basic medium, strongly alkaline medium, when it participates in strongly alkaline medium, it gets converted into MnO4 dinegative. Why am I telling you all this? Have a look, guys. First thing, the oxidation state of manganese over here is +7. The oxidation state of manganese over here is +2. Here it is +4. Here it is +6, right? Now, for example, imagine that this KMnO4, it is participating in the acidic medium. In the acidic medium, is the oxidation state of manganese increasing or decreasing? +7 to +2, decrease in the oxidation state. Decrease in the oxidation state is something which we call as a reduction. And the one which undergoes reduction, that is the oxidizing agent. So KMnO4 in acidic medium, it is behaving like the oxidizing agent, right? Now, what do I want? I want the N factor of KMnO4. I want the n factor of KMnO4. In which medium? In acidic medium. It has to be equal. In acidic medium, it will be equal to change in the oxidation state of manganese, which is equal to final oxidation state minus initial oxidation state. The value has to be 5, right? So this 5 I won't be calling as, no doubt, manganese is undergoing change in oxidation state. But I won't be saying that 5 is the n factor of manganese. No, I'll say 5 is the n factor of entire KMnO, right? 5 is the n factor of entire KMnO4. Similarly, if I want the n factor of KMnO4, in neutral medium, it has to be equal to change in the oxidation state of manganese. Final minus initial. Final minus initial. The value comes out to be 3. So 3 is the n factor of KMnO4 in neutral medium. Why am I not multiplying this 3 with any subscript? Because over here we have got only one manganese. So no need of subscript. Right? Yeah? Perfect. Now similarly, if I talk about the n factor of KMnO4, in strongly alkaline medium, it will be equal to change in the oxidation state. Final minus initial. Final minus initial. The value has to be 1. So 1 is the n factor of KMnO4 in strongly basic medium, strongly alkaline medium. So quickly, let me know in the chats if you got to know the n factors of KMnO4 in acidic, neutral and basic medium. Quickly, yes or no in the chats. Quickly, yes or no in the chats. And you have to remember them. No need to calculate them all the time. Do remember the n factor of KMnO4 in acidic, neutral and basic medium. Directly from now onwards. No need to remember them. Again, I'm telling you. There was a question asked long back in your JEE examination. That's a proper NEET standard question. Right? You were supposed to calculate the ratio of equivalent weights of KMnO4. The ratio of equivalent weights of KMnO4 in acidic medium, in neutral medium, in basic medium. This is the ratio of equivalent weights you had to calculate. Right? What is the equivalent weight? Molar mass divided by n factor. Let's assume the molar mass of KMnO4 is m divided by n factor of KMnO4 in acidic medium is 5. Molar mass of KMnO4 m, neutral medium n factor is 3. Molar mass divided by n factor in basic medium, that's 1. Right? Take the ratio. M everywhere cancelled. So it's 1 by 5 is to 1 by 3 is to 1 by 1. Correct? But the answer was not written in this format. The answer was written in terms of whole numbers. So what I'll be doing, I'll be taking the LCM of denominators. If I take the LCM of denominators, LCM of 5 and 3 comes out to be 15. So multiply this term with 15, multiply this term with 15, even multiply this term with 15. So 5, 1, 5, 3. So this is 3 is to 5 is to 15. So this is the ratio of the equivalent weight of KMnO4 in acidic, neutral and basic medium. Right? Is this clear to everyone? This was about what? This was about KMnO4. Now something which you have to remember about K2Cr2O7 as well. Something which we have to remember about K2Cr2O7 as well. Only one thing. Only one thing. K2Cr2O7. It is again a strong oxidizing agent. And my dear students, in acidic medium, this K2Cr2O7, it gets converted into Cr tripositive. This is something which you need to remember. In acidic medium, your K2Cr2O7, it gets converted into what? It gets converted into Cr tripositive. Now, if I ask you, what is the n factor of K2Cr2O7 here? How you are going to do it? Again, the same procedure. The oxidation state of chromium here is plus 6. The oxidation state of chromium here is plus 3. Right? What is happening? Increase or decrease? Decrease in the oxidation state. Decrease in the oxidation state means reduction, gain of electrons. Right? Gain of electrons. Now, guys, have a look. First thing, I'm asking you to calculate n factor of K2Cr2O7 in the above reaction. In the above reaction, it will be equal to change in the oxidation state of chromium, which will be equal to final oxidation state of chromium minus initial oxidation state of chromium. The value has to be 3. Now you tell me, should I be calling this 3 as the N factor of K2Cr2O7? I won't be calling it as the N factor. I won't be calling this 3 as the N factor. Why? Tell me why. This 3 is the change in the oxidation state for 1 atom of chromium. But do I have 1 atom of chromium or 2 atoms? Or 2 atoms. Now it will come out to be 6. So 6 is basically the N factor of your K2Cr2O7. I hope it's clear to everyone. The 6 is basically your N factor of K2Cr2O7. Now I hope you exactly got the concept of how do we get the N factors of oxidizing and reducing agents. Now it's time to utilize the concept properly. So dear students, mark the heading as some important reactions of KMnO4. Some important reactions of KMnO4. In which medium? In acidic medium. Mark the heading. Mark the heading. Some important reactions of KMnO4 in acidic medium. Whatever reactions I'm going to give you now, these are actually which you study in your D and F block elements, right? But let's complete that here only so that it will help us in the equivalent weight concept as well. Okay, so see guys. First of all, you know, when you talk about your KMnO4, in acidic medium, KMnO4 gets converted into Mn di positive. That's something which every one of you would be knowing, right? Now, this KMnO4 is an oxidizing agent. It is an oxidizing agent. Number 1. KMnO4, it converts Fa di positive into Fa tri positive. KMnO4 in acidic medium, it converts Fe di positive into Fe tri positive. This is first thing which you need to remember. It converts Fe di positive into Fe tri positive in acidic medium. Number 2, it converts oxalate ion C2O4 di negative to carbon dioxide. This is the second reaction KMnO4 shows in acidic medium. It converts oxalate into carbon dioxide. Third one, it converts H2O2 into O2. It converts H2O2 into O2, right? Fourth reaction, it converts H2S into S. H2S into S. One more reaction. It converts Sn di positive to Sn plus 4. Sn di positive to Sn plus 4. And my dear students, at the end, it converts I negative to I2. It converts I negative to I2. So these are the things which you have to remember first of all. Then only you can solve the questions. KMnO4 in acidic medium, it converts Fe di positive to Fe tri positive, oxalate to carbon dioxide, H2O2 to O2, I negative to I2, Sn di positive to Sn plus 4, right? H2S to H2S, H2S to S, right? Now, why am I telling you to remember these things? So that you don't have to mug up the reaction, so that you can write the reactions on your own. And how exactly you are going to write the reactions? Have a look. First of all, the first reaction. I'm talking about KMnO4. And KMnO4, we got to know, it converts Fe di positive. It converts Fe di positive. In which medium? Acidic medium. Into what? It converts Fe di positive into Fe tri positive. And you know, in acidic medium, it gets converted into Mn di positive. And with that, I'll be writing water. Nothing else. This is a complete reaction. It is a complete reaction. The same KMnO4, it converts oxalate. It converts oxalate ion. In which medium? Acidic medium. Into what? Carbon dioxide. And itself gets converted into Mn di positive. With that, you'll be writing water as well. Perfect. The same KMnO4, it converts H2O2. In which medium? Acidic medium. Into what? O2. Itself gets converted into Mn di positive. With that, you'll be writing water as well. Right? Similarly, the next reaction, I think all the other reactions you can easily write now, yeah? KMnO4, it converts H2S. In which medium? Acidic medium. To what? Sulfur. Rest, everything same. KMnO4, it converts Sn di positive. In which medium? Acidic medium. Into what? Sn plus 4. itself gets converted into Mn di positive plus water. Similarly, KMnO4, it converts I negative. In which medium? Acidic medium. To what? I2. Itself gets converted into Mn di positive and water. So no need to mug up the reaction. You just have to remember KMnO4 converts what into what. That's all. That's all. Yeah? Done and dusted? Perfect. Now, people, similarly, there are some reactions of K2Cr2O7 as well. Some important reactions of K2Cr2O7. Important reactions of K2Cr2O7. And in which medium? In acidic medium only. In acidic medium only. First of all, you know, your K2Cr2O7 in acidic medium, it gets converted into Cr tri positive, right? Yeah? Jennifer, basically, I'm unable to find the mole concept PDF, okay? I tried it a lot, but that is there in the studio of Bangalore, but right now I'm in Kashmir. I tried to get it, but I was unable to. So please and please watch the session again to make the handwritten notes for the mole concept. All the other chapters I'm giving. Okay? Perfect? All right, so now I'm basically talking about the important reactions of K2Cr2O7 in acidic medium. Okay. My dear students, no change at all. Whatever reactions I showed you for KMnO4, same reactions you'll write for K2Cr2O7 as well. Same things. K2Cr2O7, it converts Fe di positive to Fe tri positive in acidic medium. It converts Sn di positive to Sn plus 4 in acidic medium. It converts H2O2 to O2 in acidic medium. It converts H2S to sulfur in acidic medium. It converts oxalate ion C2O4 dinegative to carbon dioxide in acidic medium. And it converts I negative to I2 in acidic medium. Now you should be able to write the reactions as well. You should be in a position to write the reaction now. See. First of all, the reaction is like this now. K2Cr2O7. It converts Fe di positive in acidic medium into Fe tri positive. Itself gets converted into Cr tri positive. And with this, you'll be writing water as well. Done and dusted. Nothing else. Right? Similarly, K2Cr2O7. It converts Sn di positive in acidic medium into what? Sn plus 4 plus this remains the same. Okay. Similarly, K2Cr2O7 converts H2O2 in acidic medium into what? Into O2. Rest, everything remains the same. I'm damn sure all the other reactions you can write on your own. Can you? My dear students, can you? All the other reactions, can you write it on its own? Quickly in the chats, quickly. Quickly let me know in the chats. All the reactions you can write on your own, right? Yes or no in the chats? Perfect. Now let's try to do some questions. Question number 1. Calculate the equivalent mass of I2 in the reaction. Calculate the equivalent mass of I2 in the reaction. So, equivalent mass of I2 will be equal to molar mass of I2 divided by n factor of I2. Correct? So, basically, we have to get the n factor. Right? We have to get the n factor of I2. How exactly? See. First thing, the oxidation state of iodine over here is 0. The oxidation state of iodine over here is plus 5. Correct? We need to calculate the n factor of I2. It has to be equal to. change in the oxidation state of iodine. Final oxidation state minus initial oxidation state. The value comes out to be 5. This 5 is the change in the oxidation state of one atom of iodine. But over here I have 2 atoms. So the value comes out to be 10. So 10 is the n factor of I2. 10 is the n factor of I2. Now, my dear students, in the same reaction, if they ask you to calculate the n factor of IO3 negative, how you'll be doing that? Calculate the n factor of IO3 negative, right? Now you'll reverse the things. See how? You'll be calling this as the initial oxidation state. You'll be calling this as the final oxidation state. So final minus initial. Final is 0. Initial is plus 5. Change is 5. 5 is the change in the oxidation state for one atom of iodine. But over here I have only one atom. So this is the n factor. The one whose n factor has to be calculated, you have to look at that at its subscript. Over here we were supposed to calculate the n factor of I2. That's why I checked the subscript of iodine. Over here it was 2. I multiplied with 2, right? N factor of IO3 negative. So I have to check the subscript of this iodine. It's 1. So I did not multiply at the end with anything. I hope it's clear. Number 1. So you got the n factors. You can easily calculate their equivalent weights. Okay. Number 1. Number 2. Second question. Calculate the n factor of N2H4 in this reaction. N2H4. What do you think? Nitrogen, its n factor here will be minus 2. Right? It will be minus 2. Nitrogen over here, its n factor will be plus 5. Sorry, I mean oxidation state will be plus 5. My bad. Okay. Oxidation state here is minus 2. Here it's plus 5. I want to calculate the n factor of N2H4, which has to be equal to change in the oxidation state. Final minus initial. Final is plus 5. Initial is minus 2. The value comes out to be 5 plus 2, 7. This 7 is the change in the oxidation state for one atom of nitrogen. But over here I have 2. So 7 2s comes out to be 14. So 14 is the n factor of N2H4 in this reaction. Correct? If I ask you, what about the n factor of HNO3 in this reaction? N factor of HNO3 in this reaction. HNO3. Then I have to reverse the things. I'll be calling this as initial. I'll be calling this as final. So it will be final minus initial. The value comes out to be 7. This 7 is the change in the oxidation state for one atom of nitrogen. And over here, I've got only one nitrogen. So it is the n factor only. Okay. Perfectly done. Right. Tell me the n factor of IO4 negative here. N factor of IO4 negative. Quickly. Okay, iodine over here is in plus 7 oxidation state. Here it is in 0 oxidation state. Calculate the change. Final, which is 0, minus initial, which is plus 7. The value comes out to be 7. So 7 is the change in the oxidation state for one atom of iodine. And over here I've got only 1. So 7 is its n factor. Right? I hope you're getting all these things. Okay. What about the n factor of this VO? N factor of vanadium oxide will be equal. Oxidation state of vanadium here is plus 2. Here it is plus 5. So calculate change. Final minus initial. The value comes out to be 3. Right? 3 is the change in the oxidation state for one atom of vanadium. So 3 is its n factor. Done? Done? Okay, one more question. What about the n factor of this particular species over here? I hope you remember why am I teaching the n factor? To calculate equivalent mass of different substances. Okay, to calculate equivalent mass of different substances. Now guys, have a look. Calculate the oxidation state of iron over here. How much it's going to be? Let's assume it as X, right? And how many? 0.94. Plus oxygen will show minus 2 oxygen state, net charge is 0. So X after solving comes out to be plus 200 divided by 94, right? Plus 200 by 90. This is basically the oxidation state, which you call as average oxidation state of iron here, right? What about this one? The oxidation state of iron right here is plus 3. Okay, this is the initial, this is the final. Now, how do we get the n factor? N factor of this particular species will be equal to change in the oxidation state. Change is final oxidation state minus initial oxidation state. Final minus initial, right? Whatever value you'll be getting. Should I be calling it as the N factor? No. It will give me change in the oxidation state for one atom of iron. But do I have 1 or 0.94? I've got 0.94. So multiply it with 0.94 at the end, you'll be getting the N factor of this particular species. Let me know in the chats if every single thing is clear. Let me know in the chats if every single thing is clear. Quickly. Quickly, guys, everyone. Everyone means everyone. Yeah? Perfecto. Okay. One more thing, guys. One more thing. There are certain substances which can sometimes behave like the oxidizing agent and sometimes they can behave like the reducing agent. There are some substances which basically show the dual nature. Sometimes they'll be behaving like the oxidizing agent and sometimes they'll be behaving like the reducing agent. And three important substances we have to remember. One is your H2O2. It shows dual nature. One is HNO2. Another one is FeSO4. These are three species which shows the dual nature. That means in some reactions, it'll be behaving like the oxidizing agent. In the other reaction, the same species will be behaving like the reducing agent, right? So let's see what exactly they do. H2O2, it sometimes gets converted into water and sometimes it gets converted into O2, right? If I ask you what is the oxidation state of oxygen here, it's -1, peroxide. Oxidation state of oxygen here, -2. Here, it is 0. Now you tell me, -1 to -2, is it increase or decrease in the oxidation? It is decrease in the oxidation state. Decrease in the oxidation state is something which we call as a reduction. And the one which undergoes reduction, that's called as the oxidizing agent. So when H2O2 gets converted into water, it behaves like the oxidizing agent, right? And how do I calculate N factor of H2O2 when it acts like the oxidizing agent? It's going to be change in the oxidation state. Final minus initial, a mod. That will give you the change in the oxidation state for one atom of oxygen. But here we have 2. So multiply with 2 and eventually you'll get the N factor of H2O2 as 2. That's something which we already know. Similarly, when it acts as the reducing agent, it gets converted into O2 and its N factor at that time will become 2. You can calculate it. Change in the oxidation state multiplied with subscript. That's it. Similarly, HNO2. When it behaves like the oxidizing agent, it gets converted into NO, wherein the N factor of HNO2 comes out to be 1. You know how to calculate it now. That's why I'm not teaching you this again. To do the change in the oxidation state and multiply, etc. That you know now, right? Similarly, when it gets converted into NO3 negative, this HNO2, it behaves like the reducing agent, where its N factor can be 2. And we have discussed in detail how to calculate it. Similarly, FeSO4, when it behaves like the oxidizing agent, it gets converted into Fe. When it behaves like the reducing agent, it gets converted into Fe tripositive. So as the oxidizing agent, the N factor of FeSO4 is 2. As the reducing agent, N factor of FeSO4 is 1. So these are some species which show the dual nature, right? Perfect. Now, guys, now there is something important. Till now, I showed you only those compounds. I showed you only those oxidizing or reducing agents wherein the oxidation state of only one element was changing. Till now, I showed you only those compounds wherein oxidation state of only one element was changing. And we were calculating the change in the oxidation state of that element, right? But there can be certain compounds wherein oxidation state of more than one element can change. There can be certain compounds wherein oxidation state of more than one element can change in a reaction, right? And over here, I'm going to show you one category. N factor of a compound in which oxidation state of more than one element simultaneously either increases or decreases. N factor of those compounds in which oxidation state of more than one element simultaneously either increases or decreases. Have a look. This is the example of that. This is the example of that. Understand. First of all, get the oxidation state of everything. See guys, this is oxalate, C2O4 di negative. So iron has to be di positive, right? Now calculate the oxidation state of carbon. Plus 2 plus 2x minus 8 is equal to 0. X value is plus 3. Oxidation state of iron over here, plus 3. Oxidation state of carbon over here, plus 4. Correct? This is something which is understood. Now you tell me, is the oxidation state of iron changing? Yes. And how is it changing? It's increasing. Plus 2 to plus 3. Is the oxidation state of carbon changing? Yes, it's changing. How does it change? It's also increasing. Can I say this particular compound is the example of the compound in which oxidation state of more than one element simultaneously increases? Simultaneously increases. How do we calculate its N factor? See guys, whenever you see a compound in which oxidation state of more than one element simultaneously increases or simultaneously decreases, how do we calculate the N factor? It has to be equal to mod of N1 plus N2. In short, what is this N1? What is this N2? See guys, iron is changing from plus 2 to plus 3. So the change in the oxidation state of iron has to be final minus initial. That has to be 1, right? N1 value is 1. What about N2 value? Change in the oxidation state of carbon. This is the final, this is the initial. So final minus initial, the value comes out to be 1. 1 is the change for one atom of carbon, but over here I have 2. So N2 value is 2. If you got N1, if you got N2. So N factor of this particular species, N factor of this particular species will be equal to N1 plus N2. That will be equal to 3. I hope you got it. I hope you got it. Yeah? Perfect. Perfect, guys. Right? This was first example. Let's have a look on the second example. One more example. First of all, this is one sulfur atom. So copper will be plus 1 and this will be minus 2. Wahi pehle wala crisscross thing, right? What about the oxidation state of this copper? It's plus 2. This sulfur, it's plus 4. You know it, correct? Now check what is happening. Plus 1 to plus 2, increase in the oxidation. Minus 2 to plus 4, increase in the oxidation state. So can I say this is the compound in which oxidation state of two elements is simultaneously increasing? How do I calculate its N factor? It's again going to be mod of N1 plus N2. Mod of N1 plus N2. Now what is N1? Plus 1 to plus 2. Change, final minus initial. The value comes out to be 1. 1 is the change for one atom, but I have 2. So N1 value is 2. Right? Similarly, minus 2 to plus 4. Minus 2 to plus 4. Change. Final is plus 4. Minus. Initial is minus 2. So 4 minus minus 2 comes out to be 6. So 6 is the change in the oxidation state for one atom of sulfur. And I have got one atom only. So N2 value is 6. So N factor of this compound will be N1 plus N2. 6 plus 2 is 8. So this is the N factor of Cu2s. Right? This is the N factor of Cu2s. Perfect? Perfect? Yeah? Okay. If I ask you what is the N factor of the Cu dipositive, you'll reverse it. This becomes initial and this becomes final. Final minus initial, the value is 1. 1 is the change for one atom. So its N factor has to be 1. Right? What is the N factor of SO2? Reverse it. Plus 4 to minus 2. Plus 4 to minus 2. Change. Final minus initial. The value comes out to be 6. 6 is the change for one atom. We have got only 1. So its N factor is 6. I hope all these things you can do. Yeah? Right? I think all these things you can do now. Okay, one more for example I'm giving you. First of all, calculate the oxidation states. 3, keep it here. 2, keep it here. Bismuth, 5, sulfur, 0. Plus 3 to plus 5, increase. Minus 2 to 0. Minus 2 to 0, increase. calculate the n factor of this particular substance. It's equal to n1 plus n2. What is n1 and what is n2? Say plus 3 to plus 5. Calculate change. Final minus initial. The value comes out to be 2. 2 is the change for one atom, but I have two atoms. So 2 to 0 comes out to be 4. Minus 2 to 0. What is the change? Final minus initial. The value is 2. 2 is the change for one atom, but I have 3. So 2 3s are 6. N2 is 6. So N1 plus N2 comes out to be 10. So this is the N factor of the compound. Yes? Perfect? Perfect, guys? I hope it's clear. I hope it is clear, right? Now, guys, just a second. Just a second. Okay. So till now, what was I talking about? We were calculating the N factor of those substances in which the oxidation state of more than one element simultaneously either increases or decreases, right? Perfect. Now, there can be some compounds as well wherein the oxidation state of one element will increase and another one will decrease. That can be one more possibility, right? One possibility is both the elements simultaneously increases. One possibility simultaneously decreases. One will be one increases, one decreases. Okay? And we have already discussed N factor of substances in which more than one element's oxidation state simultaneously increases or simultaneously decreases. It is N1 plus N2. Now, what about the one wherein the oxidation state of one element increases, another one decreases? How do we calculate its N factor? Do remember, N factor of that particular substance will be mod of N1 minus N2. Mod of N1 minus N2. Okay? Now understand. This 3 will be the charge of iron. This 2 will be the charge of sulfur. Iron here is in plus 2 oxidation state. Sulfur here is in plus 4 oxidation. Agreed? Yes? Now after this, my dear students, have a look. Iron is changing its oxidation state from plus 3 to plus 2, decrease in the oxidation. Minus 2 to plus 4, increase in the oxidation state. So understand. Oxidation state of one element is decreasing, another element is increasing. So N factor of this particular substance has to be equal to mod of N1 minus N2. And N1, N2, you already know how to calculate. What is N1? Plus 3 to plus 2. Change in the oxidation state is 1. 1 is the change for one atom, but I have 2. So it has to be 2 into 1. Correct? Similarly, minus 2 to plus 4. Change. Final minus initial. So 4 minus minus 2 comes out to be 6. 6 is the change for one atom, but I have got 3 atoms. So 6 3s are 18. So N2 value is 18. So I got N1, I got N2. If I got N1 as well as N2, can I calculate its N factor now? It has to be equal to mod of N1 minus N2. That answer is going to be 16. So its N factor has to be 16. If you got its N factor, molar mass divided by N factor. Done and dusted, right? Perfect. I hope it is super clear to you. One question I'm going to give you as the homework. This is one question which I'm giving you as the homework. Do let me know the answer of this question in the comment section at the end of the session. Do let me know the N factor of this particular substance. Its structure already we know. I have given you the structure of it already. Right? Can you do it? Say yes or no. Can you do it? Say yes or no in the chats. Quickly, everyone. Whosoever is watching me right now. Will you be able to do it? Yeah? Sure? Like, are you super confident that you will be able to do it? Are you super confident about that? This is something which I'm giving you as the homework. All right. Now there is one last category of n factors. What is that? N factor of the species which undergoes disproportionation. N factor of the species which undergoes disproportionation. Let's get to know what is meant by that. N factor of the species which undergoes disproportionation. See guys, we have got a reaction over here. If I ask you what is the oxidation state of bromine over here, it is 0. What is the oxidation state of bromine right here? It's +5. Oxidation state of bromine right here, it's -1. Now see, 0 to +5, increase in the oxidation state. 0 to -1, decrease in the oxidation state. Can I say this is a reaction in which oxidation state of same element is simultaneously increasing as well as decreasing, right? Oxidation state of same element is simultaneously increasing as well as decreasing, right? So it is self-oxidation and self-reduction. I'll say some part of Br2 will undergo oxidation and some part of Br2 will undergo reduction. So that particular reaction in which oxidation state of same element simultaneously undergoes oxidation as well as reduction, we say that species undergoes disproportionation. We say that particular species undergoes disproportionation. And whenever in a particular reaction, a species undergoes disproportionation, how do we calculate its n factor? Its n factor is calculated as simple n1, n2 divided by n1 plus n2. This is the result which you guys are going to use to calculate the n factor of the substance which undergoes disproportionation. Yeah? Now guys, have a look. Let's get the value of n1 and n2. Okay, let's get the value of n1 and n2. 0 to +5. What is the change? Final minus initial. The value comes out to be 5. But that 5 is the change in the oxidation state for one atom of bromine. But how to? 5 2s are 10. N1 value is 10. N1 value is 10. Right? Similarly, 0 to -1. Change. Final minus initial. The value comes out to be 1. 1 is the change for one atom. But how to? N2 value comes out to be 2. So you got N1, you got N2. Get the overall n factor. So N1 is 10, N2 is 2. So 10 into 2 divided by 10 plus 2. The value comes out to be 20 divided by 12. Right? So it comes to be 4543. So this is the n factor of your Br2 in the reaction. Right? So if I ask you, what is the equivalent weight of Br2? You will say equivalent weight of Br2 is molar mass of Br2 divided by its n factor, which is 5 by 3. So the answer has to be 3m divided by 5. This is the equivalent mass of Br2 in this particular reaction. I hope it's clear. I hope it's clear to you. Okay? All right. One more, for example. Let's say I'm writing a reaction like this. H2O2, it gives H2O plus O2. This is a reaction, and I'm asking you to calculate the equivalent mass of H2O. How do I get the equivalent mass of H2O? It has to be molar mass of H2O2 divided by n factor of H2O. Right? Now guys, understand. Oxidation state of oxygen here is -1. Here it is -2. Here it is 0. Right? So -1 to -2, decrease in the oxidation. -1 to 0, increase in the oxidation state. So can I say the oxidation state of same element is decreasing as well as increasing? So I'll say this whole substance over here undergoes what? Undergoes disproportionation. If it undergoes disproportionation, so what about its n factor then? So I would say n factor of H2O2, it has to be equal to N1, N2 divided by N1 plus N2. This is how you're going to do it. Yeah? This is how you're going to do it. Now calculate N1, calculate N2. -1 to -2, the change is 1. 1 is the change for one atom, but how 2? So N1 value over here is 2. -1 to 0, the change is 1. 1 is the change in one atom, but how 2? So N2 value is also 2. So N1 is 2, N2 is 2. So 2 multiplied by 2 divided by 2 plus 2. The value comes out to be 1. So I would say the n factor of H2O2 in this reaction is 1. And if the n factor of H2O2 is 1, So its equivalent mass has to be equal to molar mass of H2O2, which is 34 grams, divided by n factor, that's 1. So the answer will be. Is this absolutely clear to everyone? Yeah? Is it clear to everyone, people? Quickly. Is it clear to everyone? This was all about your equivalent mass and n factors. I hope you liked the topic, right? I did not skip a thing, and you are not going to get something apart from this in the examination, okay? Same things will you get. So now we are going to enter into one more part, that's balancing. I think before we do the balancing, let's take one more break, okay? We'll take a dinner break and we'll get back. 3 topics I have to discuss. Balancing, redox titration, most important, redox titration, and volume strength of H2O2. Right? So, by the way, do you remember we took one break at 6:41 and another break we are taking at 8:41? Wow. That's nice. Synchronized. Okay, so class resumes at what's the time now? 9, huh? 9 p.m. 3 topics left. Balancing, titration, which is also what you call as equivalent concept, and volume strength. Volume strength of H2O2. But my dear students, I would want all of you to be back on time. Yeah? To be back on time. Prasanna, basically, it's completely your call whether you want to take the batch or not. See, on YouTube, we just teach, right? In the batch, in the paid batch, we teach. Apart from that, whatever doubts you have, you ask us in the session. You get like the chapter-wise mock tests, all those things you get. Over here, we just teach. But content-wise, it will be same. Whatever I teach in the paid batch, I teach here the same thing. I do not teach anything extra there, right? But it's about the aftercare, basically, right? The after one-on-one mentorship, that is there in the paid batch, not here on YouTube. That's the part which is missing on YouTube, basically, is a drawback of YouTube. Perfect. So let's take a break, but I would want every one of you to be back at 9, okay? Till then, you guys have your dinner. Bye-bye. Guys, am I audible? Everyone is back? Yes? So now 3 topics are left. One is your balancing of reactions, balancing of redox reactions. Number 2, titration. Number 3, the volume strength, right? Let's try to cover these topics. Just a second, guys. Okay, first of all, let me tell you one thing. There are basically many methods by means of which we can balance the redox reaction. Okay? There are many methods by means of which we can balance the redox reaction. But we are only going to remember the simplest method, right? And the simplest method by means of which we can balance the redox reactions in lesser time, that is oxidation number method. So I will be teaching you balancing of redox reactions through oxidation number method in acidic and basic medium. This is something I'm going to teach you, right? Because what is our main motive? To balance the reactions, right? Then which method you want to apply, that's completely your choice. But I would suggest you guys to apply oxidation number method, which is the easiest way, right? So I'll be only teaching you the oxidation number method, through which we shall balance the reactions in lesser time, right? Perfect. Let's start with the first thing. Balancing of redox reactions through oxidation number method in acidic medium, right? In acidic medium, how do we balance the reactions? Through oxidation number method. Let's have a look on it. Let's see exactly what all steps we have to follow. Okay? Have a look, people. First of all, the first step always is to get the oxidation state. The oxidation state of manganese here is +7. Here it is +2. Here it is +2. And here it is +3. Okay? These are the oxidation states of different elements, which I mentioned over here. Number one. Number two, just calculate the n factors of these reactants. N factors of these reactants. +7 to +2, change is 5. So its n factor has to be 5, right? +2 to +3, change is 1. So its n factor has to be 1. So you got the n factors of the reactant. Well, after getting the n factors of the reactants, just crisscross these n factors. What does that mean? This one, which is the n factor of Fe di positive, you'll make it the stoichiometric coefficient of MnO4 negative. This 5, you'll make it the stoichiometric coefficient of Fe di positive. So after getting the n factors, I just crisscrossed them, right? Number two, after crisscrossing the n factors, balance all the atoms except hydrogen and oxygen. Balance all the atoms except hydrogen and oxygen. 1 manganese, so 1 manganese on this side. 5 iron, so 5 iron on this side. So first of all, I calculated the n factors of reactants. Then I crisscrossed the n factors. Then I balanced all the atoms except hydrogen and oxygen, right? Now, my dear students, we are going to balance the oxygen atom. And let me tell you, oxygen atoms are balanced by adding water molecules on that side, which will be oxygen deficient. We'll be balancing now the oxygen atoms by adding water molecules on that side, which will be oxygen deficient. Now you tell me, how many oxygen atoms are there on the reactant side? 4 oxygen atoms. Is there any oxygen atom on the right side? There is no oxygen atom on the right side. So which side is oxygen deficient? Right side is oxygen deficient. There is the deficiency of 4 oxygen atoms, right? And the side which is oxygen deficient, just add water molecules on that side. So how many water molecules I'm going to add on that side? This side is oxygen deficient and there is oxygen deficiency of 4. So I'll be adding 4 water molecules on this side, right? Check whether the oxygen is balanced. Yes, now the oxygen is balanced. After oxygen, you'll be balancing the hydrogens by adding H positives on that side, which is hydrogen deficient. Is there hydrogen on this side? No. Is there any hydrogen on this side? Yes, 8 hydrogen. So left hand side is hydrogen deficient. So I'll be adding 8 H positives on left side. The reaction is automatically balanced. Now it is a balanced chemical equation. Isn't it simple? Isn't it simple, people? For example, one more reaction I'm taking. Let's say you have got MnO4 negative plus Sn di positive. In acidic medium, it gives Mn di positive plus Sn plus 4. Let's balance this reaction in acidic medium. Let's see if you can do it or not. The first thing, calculate the oxidation states. +7, +2, +2, +4, right? Get the n factors of reactants. N factor of MnO4 negative. +7 to +2, change is 5. So its n factor has to be 5. +2 to +4, change is 2. So its n factor has to be 2. So we got the n factors of the reactants. After getting the n factors of the reactants, what are we supposed to do? Just crisscross these n factors. This 2 has to be the stoichiometric coefficient here. This 5 has to be the stoichiometric coefficient here, right? So after crisscrossing the n factors, balance all the atoms except hydrogen oxygen. Except hydrogen oxygen. 2 manganese this side, so 2 manganese on this side. 5 tin on this side, 5 tin on this side, right? Now, We are balancing in acidic medium. It is the time to balance oxygen now by adding water molecules. Do you see oxygen on this side? Yes. How many? 2 4s are 8. 8 oxygen atoms on left side. Is there any oxygen atom on right side? No. So right side is oxygen deficient. And there is 8 oxygen deficiency, right? So I'll be adding water molecules on this side, right, to balance the oxygens. Now the oxygens are balanced. Since the oxygen atoms are balanced, now it is the time to balance hydrogens. On left side, do you see any hydrogen? No. On right side, do you see any hydrogen? 16 hydrogens. So which side is hydrogen deficient? It is the left side which is hydrogen deficient. And how many hydrogen deficiency is there? 16 hydrogen deficiency. So add 16 H positive on this side. Now it's a balanced chemical equation. Is it clear? It's simple, right? Let's try to balance one more reaction. For example, you have got Cr2O7 dinegative, Cr2O7 dinegative, right? Plus C2O4 dinegative. In acidic medium, it gives carbon dioxide, right? And you get Cr positive. Perfect. Let's try to balance this reaction in acidic medium. How exactly? You know it. First of all, we'll be getting the N factors. And you know how to get the N factors. N factor of this particular species, 6. N factor of this particular species, 2. Right? You know how to get the N factors of reactants. Right? Now crisscross these N factors. This 2 will be the stoichiometric coefficient here. This 6 will be the stoichiometric coefficient here. Right? After crisscrossing with the N factors, balance all the atoms except hydrogen, oxygen. 4 chromium on this side. So 4 chromium on this side. 6 to the 12. 12 carbon on this side. So 12 carbon on this side as well. Now it is the time to balance oxygen, right? How many oxygen atoms are there on left hand side? 7 2s are 14. 14 plus 24. 6 4s are 24. 24 plus 14 comes out to be 38. And how many oxygen atoms on this side? 12 2s are 24. So 24 oxygens on right. So which side is oxygen deficient? Right side is oxygen deficient. And how much oxygen deficiency is there? 38, 24. That means I'll be adding 14 water molecules on this side to balance the oxygen atoms. Now, since the oxygen atoms are balanced, it is the time to balance the hydrogens now, right? Now, how many hydrogens on right side? 28 hydrogen atoms. No hydrogen atom on this side. So make it 28 times H positive. Now, it is a balanced chemical equation. Anyways, you can divide the reaction throughout by 2 as well. This will become 14, this will become 1, this will become 3, this will become 6, this will become 2, and this will become 7. That will be one more way of writing the balanced chemical equation. Is it clear? Isn't it simple? Isn't it simple, people? So this is balancing of reactions through oxidation number method in acidic medium. Is it clear? Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students. Quickly. Quickly. Now, what exactly we are going to do? Let's see exactly how do we balance the reactions through oxidation number method. But in which medium? In basic medium. In basic medium. The first 3-4 steps are same. The first 3-4 steps are same. See where the difference lies. Let's have a look on the first steps. Oxidation state here is 0. Here it is plus 5 iodine. Here it is minus 1. And here it's plus 7. Right? The oxidation state of iodine is plus 7. Now, my dear students, tell me one thing. N factor of Cl2, 0 to minus 1. Change is 1. 1 is the change for one atom, but I have 2. So it's N factor is 2. Plus 5 to plus 7. Change is 2. So its N factor is 2. So I got the N factors of all the reactants. After getting the N factors of all the reactants, what are we supposed to do? We are supposed to crisscross them. This 2 has to be the coefficient here. This 2 has to be the coefficient here. Right? Perfect. Now after that, what do? After that, we try to balance all the atoms except hydrogen, oxygen. 2 2s are 4 chlorine on this side. So this has to be 4. 2 iodine on this side. So this has to be 2. Right? Done. Now, my dear students, since we are going to balance the reaction in basic medium, now things change. In acidic medium, now we were supposed to balance oxygen. But in basic medium, we are going to balance the negative charge. We are going to balance the negative charge. Negative charge is balanced by adding OH negatives. on that side which is negative charge deficient. What does that mean? See, there is no charge on chlorine here, but on 1IO3, the charge is -1. So on 2IO3, the charge has to be -2. So on reactant side, the charge is -2. Check on product side. On 1 chlorine, the charge is -1. So on 4 chlorine, it has to be -4. On 1IO4, the charge is -1. On 2, it has to be -2. So -4, -6 comes out, -4, -2 comes out to be -6. So, right? So we got to know on left-hand side, the total negative charge is -2. On right-hand side, the total negative charge is -6. Now you tell me, which side is negative charge deficient? -2 total charge on left-hand side, -6 on right-hand side. Which side is negative charge deficient? I say it is left-hand side which is negative charge deficient. How much negative charge deficiency is there? 4 negative charge deficiency. So I'll be adding 4 OH negatives on this side to balance the charge. Now check, what is the charge on left-hand side now? It was -2. Now on 1 OH, the charge is -1. On 4 OH, the charge will be -4. So -4, -2 comes out to be -6. -6 is equal to -6, right? The charge is balanced. After balancing the charge, you are going to balance oxygen by adding what? By adding water molecules, right? Now check it. How many oxygen atoms are there on left-hand side? 4 plus 6, 10 oxygen atoms. So 10 oxygen atoms on left side. Right side, 4 2s are 8 oxygen atoms. If I ask you which side is oxygen deficient, you will say right side is oxygen deficient. 10 this side, 8 this side. And how much oxygen deficiency is there? 2 oxygen deficiency. So add 2 water molecules on this side, right? Add 2 water molecules on this side. You are not supposed to balance hydrogen. Hydrogen would have got automatically balanced. You can check it out. It is a balanced chemical equation. It is a balanced chemical equation. Yes? Is it clear? So how easy balancing is? Only change here is you have to balance the negative charge first by adding OH negatives. Then balance what? Then balance the oxygen atoms by adding water molecule. That's all. In acidic medium, you have to balance oxygen first, then hydrogen, right? Charge automatically gets balanced. In basic medium, you balance charge first, then oxygen. Hydrogen automatically gets balanced. Isn't it simplest? Isn't it simplest, my dear students? Isn't it simplest? Yes? Let me give you one question as the homework. Do the balancing of it through oxidation number method. Through oxidation number method, right? Can you do it? Do you want to see ion electron method as well? Or this much is enough? Do you want to see ion electron method as well? Let me just give you one example, okay, so that you'll get the idea of what ion electron method is all about. Let's see, just a second. Okay, one example I'll give you in ion electron method as well. See, balancing of redox reactions in acidic medium through ion electron method. Now guys, the first steps are same. Calculate the oxidation state of manganese. It's +7. Iron, it's +2. Manganese, it's +2. And over here, it's +3. Right? Now you need to identify which species among the two is undergoing oxidation and which species among the two is undergoing reduction. +7 to +2, decrease in the oxidation state, means reduction. So MnO4 negative is undergoing reduction. So first of all, I'll be writing the reduction half reaction. I'll be writing the reduction half reaction. In the reduction half reaction, we got to know MnO4 negative is getting converted into Mn dipositive. Right? Now, my dear students, from +7 to +2, what is the change in the oxidation state? Final minus initial, the value is 5. So basically, when MnO4 negative is undergoing reduction, is getting converted into Mn dipositive, it will be gaining 5 electrons, then only it will be getting converted into Mn dipositive. Because it's the reduction reaction. It involves gain of electrons. And how do you get to know How many electrons are gained? Simply change in the oxidation state. That gives you the idea about the gain of electrons. Now, what about the oxidation half reaction? What about the oxidation half reaction? See, plus 2 to plus 3. Plus 2 to plus 3. Increase in the oxidation state means oxidation. So, in the oxidation half reaction, it is Fe di positive, which will be getting converted into Fe tri positive, right? Plus 2 to plus 3. Increase in the oxidation state means oxidation, means loss of electrons. Now, how many electrons are lost? Check the change in the oxidation state. Final minus initial. The value comes out to be 1. So, this has to be 1 electron here, right? Loss of electrons, oxidation. Now, you tell me how many reactions we got. 2. One is reduction half, one is oxidation. If I ask you whether electrons in both the reactions are balanced or not, the electrons in both the reactions are not balanced. Here we have got 5. Here we have got 1. What we'll be doing? We'll be balancing the electron. How exactly? I'll be multiplying this reaction by number 5. By 5. So that this becomes 5 times. So that this becomes 5 times. So that this becomes 5 electrons. Right? Now I'll be adding them up. When I add them up, 5 electrons gets cancelled out. And my net reaction becomes MnO4 negative plus 5 times Fe di positive. It gives Mn di positive plus 5 times Fe tri positive. Perfect. We got it till here. Now, my dear students, since I'm balancing the reaction in acidic medium, and in acidic medium, do we balance charge first or oxygen? In acidic medium, we balance oxygen first. 4 oxygen on this side, no oxygen on this side. So add 4 water molecules. After balancing oxygen, balance hydrogen. 8 hydrogen on this side, right? 8 H positives on this side. Now it's a balanced chemical equation. Now it is a balanced chemical equation, right? One more thing. How many electrons got cancelled out? 5. That means number of moles of electrons exchanged in the net reaction. Exchanged in the net reaction, that is 5. Number of moles of electrons exchanged in the net reaction is 5. Dear students, one more thing I'll tell you. Through this method, we got to know the number of moles of electrons exchanged in the net reaction. Now see how easily you can calculate N factor. You don't have to do the other things which I told you. Change in oxidation state, leave that. One more way. First, balance the reaction. After balancing the reaction, get the number of moles of electrons exchanged. Got it? Now, calculate the N factor of MnO4 negative. How exactly? Moles of electrons exchanged divided by its stoichiometric coefficient. This is the N factor of MnO4 negative. You can check it out also. See, plus 7 to plus 2, change is 5. N factor is 5. N factor of Fe di positive. Number of moles of electrons exchanged divided by stoichiometric coefficient. 5 by 5 is 1. This 1 is the N factor of Fe di positive. Right? Now check it by your way. Plus 2 to plus 3. Change in the oxidation state is 1. Right? That 1 was the N factor. Yeah? N factor of Mn di positive. Number of moles of electrons exchanged, 5 divided by stoichiometric coefficient. That's 1. 5 by 1 is 5. N factor is 5. 5 by 5 is 1. Its N factor is 1. So this is one more way of calculating the N factor. And this is the actual way of calculating the N factor. Whatever I told you till now, those were tricks to calculate N factor. The actual way is to balance the reaction, get the number of moles of electrons exchanged, and divide those number of moles of electrons exchanged with the stoichiometric coefficient of each one. You'll get the N factor of each one. That's it. Got it? This is one more way of calculating the N factor. I hope it's clear to you. Yeah? Perfect? Perfect, guys? Okay. Let's try to balance this reaction through ion electron method. In ion electron method. See, guys. First of all, check which one is undergoing oxidation and which one is undergoing reduction. Oxidation state of chlorine right here is 0. Over here it's going to be plus 5. Right here it's going to be minus 1. And right here it's going to be plus 7. Yeah? These are the oxidation states of different elements. Now you tell me one thing. 0 to minus 1. 0 to minus 1. Decrease in the oxidation state means reduction. So let's try to write the reduction half reaction. In the reduction half reaction, your Cl2 is getting converted. Your Cl2 is getting converted into Cl negative. First of all, this is Cl2, so I'm writing 2 times over here only. Now 0 to -1, decrease. Decrease means reduction. Reduction means gain of electrons. So Cl2 will be for sure gaining some electrons. Then only it will be getting converted into Cl negative. Now how many electrons it's gaining? Final oxidation state minus initial. The value is 1. 1 is the change for one atom, but I have 2. So basically it's gaining 2 electrons. Then only it's getting converted into 2 times Cl negative. Yeah. Now guys, after that, let's talk about the oxidation half reaction. In the oxidation half reaction, as you can see, the oxidation state of iodine is changing from +5 to +7. So increase in the oxidation state means oxidation. So in the oxidation half reaction, IO3 negative is basically getting converted into IO4 negative. Now, +5 to +7, increase, oxidation, loss of electrons. How many? Final minus initial, the value comes out to be 2. Right? So IO3 negative will be losing 2 electrons, then only it will be getting converted into IO4 negative. Right? Now, dear students, are the electrons balanced over here? Yes, the electrons are already balanced. So no need to do anything. Just add the reaction. When you add the reactions, this 2 and this 2 got cancelled. This is Cl2. This is IO3 negative. It gives 2 times Cl negative. And with this, you'll be writing IO4 negative. Correct? Now, I'm balancing this reaction in which medium? I'm balancing it in basic medium. And in the basic medium, are we supposed to balance oxygen first? No. I'm supposed to balance charge first. Right? The charge on one molecule of IO3 is -1. Here it is 0. One chlorine carries charge -1, so 2 carries -2. And this is -1. So -2 -1 is -3. Perfect? Right? So on left side, the charge is -1. On right side, the charge is -3. So which side is negative charge deficient? Left side. Right? How much negative charge deficiency is there? -2. So I'll be adding 2 OH negatives on this side. 2 OH negatives on this side. After adding 2 OH negatives, the charge is balanced now. After balancing the charge, it's time to balance oxygen. How exactly? See, 2 plus 3, 5 oxygen on this side, 4 oxygen on this side. So this side is oxygen deficient. So I'll be adding 1 water molecule on this side. The oxygen is balanced. Now, if the oxygen is balanced, that means hydrogen would have got automatically balanced. Now, it is a balanced chemical equation. If I ask you, how many moles of electrons got exchanged in the net reaction? Number of moles of electrons exchanged, that's 2. If I ask you what is the n factor of Cl2, you will say moles of electrons exchanged divided by stoichiometric coefficient, that's 1. 2 by 1 is 2. So its n factor is 2. Its n factor, 2 by 1, 2. Its n factor, 2 divided by 2, that's 1. Its n factor, 2 divided by 1. Correct? I mean, this is one more way. This is the actual way of calculating the n factors. Get the number of moles of electrons exchanged, divide them with the stoichiometric coefficient of each. You'll be getting the n factor of each substance. Right? You can cross-check it by your way. How I taught you to calculate n factors easily. Right? The actual procedure for n factor calculation is you have to balance the reaction first. Right? Then later on you can calculate the n factor. The way I'm showing you right now. The simplest way is you're not supposed to balance it. Just calculate the change in oxidation state. 0 to -1. Change is 1. 1 is the change for 1, but I have 2. So 2 into 1 is 2. Its n factor is 2. +5 to +7. Change is 2. 2 is its n factor. Right? That is one more way of getting the n factors without balancing the reaction. I hope every single thing is clear till here. I hope every single thing is clear till here. Right? Now guys, one more thing. How do we balance the disproportionation reactions? Let me tell you, whenever you are supposed to balance the disproportionation reaction, you'll be balancing the disproportionation reaction always with the help of ion electron method. With the help of ion electron method. And this reaction we need to balance in basic medium. And how exactly you're going to do it? The same way as I was showing you till now. Oxidation state right here is 0, over here is -1, bromine over here is at +5 oxidation state. So 0 to -1, decrease. Decrease means reduction, gain of electrons. So what is my reduction half reaction? In the reduction half reaction, what is happening? Your Br2, it is getting converted into Br negative. Correct? Try to balance bromine here only, 2 times. Now see, 0 to -1, decrease in the oxidation state, means reduction, means gain of electrons. Now, how many electrons are being gained by this Br2 so that it gets converted into Br negative? Calculate the change in oxidation state. Final minus initial, the value is 1. 1 is the change for one atom, but I have 2, so make it 2. So Br2 will be gaining 2 electrons, then only it will be getting converted into 2 times Br negative. Now, what about the oxidation half reaction? What about the oxidation half reaction? See, 0 to plus 5 increase means oxidation, means loss of electrons. So basically, Br2 will be getting converted into BrO3 negative. Perfect, during the oxidation. So check, 0 to plus 5. What is the change? Final minus initial, value is 5. 5 is the change for one atom, I have 2. 5 2s are 10. So I'll write 10 electrons here. Not this side, sorry. Since it is the oxidation half reaction, and during the oxidation, loss of electrons takes place. So this 10 electrons has to be on this side. So Br2 will be losing 10 electrons. Then it will be getting converted into BrO3 negative. I hope everything is clear till here, right? Nowadays, students, check whether electrons are balanced in both the reactions or not. The electrons are not yet balanced. 2 over here, 10 this side. Try to balance the electrons. So what I'll be doing, I'll be multiplying first reaction by number 5. After multiplying first reaction by number 5, it becomes 5 times. This one becomes 5 2s are 10 times. This one becomes 5 2s are 10 times. Correct? Now add them up. When you add them up, this 10 and this 10 got cancelled. So my net reaction is 5Br2 plus Br2. It makes it 6Br2. It gives 10 times Br negative plus BrO3 negative. Right? Since the reaction is taking place in the basic medium. So I need to balance the charge first. Now balance the charge. On right hand side, 1 Br carries -1 charge. So 10 Br atoms carries 10 units of negative charge. 1 BrO3 carries -1 charge. So 10 minus 1 is equal to, this is -10 and this is -1. So it's -11. -11 units of charge on the right side. On left side, there is no charge. I hope you're getting it. 1 Br carries the charge of -1, right? So 10 Br will carry the charge of -10. 1 BrO3 carries the charge of -1. So -11 unit of charge on the right side. Okay. So left side, you'll be adding what? You'll be adding 11 OH negatives to balance the charge. After balancing the charge, it's time to balance the oxygen atoms. And oxygen atoms are balanced with the help of what? I think we missed something. Is that? Did we miss something? 5 Br plus Br makes it 6 Br2. It's 10 Br negative. This is BrO3, right? Is everything proper till here? This is B6 times Br2. This is 10 times. This is 1. So 10, 11. So this 11 OH. Now it's time to balance the oxygen. So oxygen here is 11. And on this side, we have got how many oxygen? We have got 3, right? So 11 oxygen on this side, 3 oxygen on this side. So this side is oxygen deficient. And how many oxygen deficiency? 8. So I'll be adding 8 water molecules on this side, right? 8 water molecules on this side. I think we messed up somewhere. Let's do it again. We messed up somewhere. Do you see any mistake over here during the addition or something? 0 to -1, the change is 1. 1 into 2 is 2, right? So Br2 plus 2 electrons makes it 2 times. So multiplied, okay, Br2. Yeah, we missed one simple thing. What was that? This was Br2. This was BrO3 negative. So this has to be 2 times here. Bromine should be balanced here only, right? We missed this. We skipped this part, right? So this has to be 2 times BrO3. This has to be 2 times BrO3, right? This is something which we skipped. Now we are going to balance the charge. See, so it is -10, it is -2, the value comes out to be -12. So -12 units of charge on the right side, no unit of charge on the left side. So I'll be adding 12 OH negatives on this side so that charge gets balanced. Since the charge is balanced, now it's time to balance the oxygen. So 12 oxygen on this side and on this side 6 oxygen. In order to balance oxygen, you'll be adding 6 water molecules, right? So this is a balanced chemical equation. Right? This is a balanced chemical equation. Now, if I ask you how many moles of electrons got exchanged, in the net reaction, you'll say 10 got cancelled, so 10 moles of electrons got exchanged. If you got to know how many moles of electrons got exchanged in the net reaction, can you let me know what is the n factor of Br2 then? Moles of electrons exchanged divided by stoichiometric coefficient, right? So it comes out to be 5 by 3. It comes out to be 5 by 3. So 5 by 3 is the n factor of Br2. Br negative. 10 divided by 10, the value comes out to be 1. 10 divided by 2, the value comes out to be 5. So these are the respective n factors of these reactants and products, right? As I told you, this is the actual way of calculating the n factors. You can do it by our trick as well. The trick which I gave you in the beginning, since it's the case of disproportionation. N1, N2 divided by N1 plus N2. There also, if you remember, 5 by 3 was the n factor of Br2. This question we did already. Is it perfectly clear? Is it clear to everyone, people? Is it clear to everyone? I hope from now onwards you can easily balance the reactions, whether in acidic medium or basic medium or wherever. Yeah? Okay? Perfectly clear? Let me know quickly in the chats. Quickly let me know in the chats if every single thing is clear till now. All right. Now, people, I'm writing the term over here as number of gram equivalents. Number of gram equivalents of a substance. Number of gram equivalents of the substance. The way we calculate number of moles of the substance, in the similar way, we calculate number of gram equivalents of the substance as well. The way we calculate moles of the substance, in the similar way, we calculate the number of gram equivalents of the substance as well. And how exactly? Number of gram equivalents of the substance is equal to mass of the substance in grams divided by equivalent mass of the substance. Right? The way we calculate number of moles, how do we calculate number of moles? Given mass of the substance divided by molar mass of the substance. Over here, it is given mass of the substance in grams divided by equivalent mass of the substance. So instead of molar mass, we use the term equivalent mass. That's it. Right? This is the first way by means of which we can calculate number of gram equivalent. Number two, I'm telling you, number of gram equivalents is equal to given mass of the substance in grams divided by equivalent mass. My dear students, given mass of the substance, I'm writing as such. Instead of equivalent mass, can't I write molar mass divided by n factor? That n factor comes into the numerator. Now, given mass by molar mass, do we call it number of moles? Yes. So, number of gram equivalents is also calculated with the help of number of moles of the substance multiplied by n factor of the substance. This is one more way of calculating number of gram equivalents of the substance. Okay? Number of gram equivalents of the substance. Number three. What is number 3? You'll have to wait for that. Okay? You'll have to wait for that. Similarly, there's a term called as milli-equivalence. Number of milli-equivalents of the substance. Number of milli-equivalents of the substance. It is always equal to mass of the substance in grams divided by equivalent mass of the substance multiplied with 1000. This is the formula by means of which we can calculate milli-equivalence of substance. One is gram equivalence of substance. Another term is milli-equivalence of substance. Right? Or instead of moles, you can write number of millimoles. Number of millimoles multiplied by n factor. Right? So these two results are very, very, very important. Why am I telling you that? You'll get the idea in some time. Right? These are the two results which I would want you guys to remember. Perfect. One term is number of moles of substance, given mass by molar mass. Now one more term is number of gram equivalents, given mass divided by equivalent mass. Right? Or number of moles of substance by n factor, multiplied by n factor of the substance. Similarly, number of milli-equivalents of substances, given mass divided by equivalent mass multiplied by 1000. Or you can say number of milli-equivalents multiplied by n factor. Right? Now guys, understand. There is something called as normality. How do we define the term normality? First of all, normality is defined as the number of gram equivalents of solute. The number of gram equivalents of solute present in 1 liter of solution. If you remember, how do we define molarity? Number of moles of solute present in 1 liter of solution. In the similar way, you are defining normality. Instead of number of moles, you are using the term number of gram equivalents. Number of gram equivalents of solute present in 1 liter of solution, right? How do we calculate normality? How do we calculate normality? Number of gram equivalents of solute divided by volume of solution in liters. Or I can write it like this. Instead of number of gram equivalents of solute, I can write mass of solute in grams divided by equivalent mass of solute. Instead of number of gram equivalents of solute, I can write mass of solute divided by equivalent mass of solute. In the denominator, you have got volume of solution in liters. If I write it in milliliters, then I will have to multiply by the number 1000 over. Correct? Yes? Now, people, I can convert it into the different format as well. I'll write mass of solute as such. Mass of solute multiplied with 1000 divided by. Over here, you can see equivalent mass of solute. Equivalent mass of solute, I can write molar mass of solute divided by n factor of solute. That n factor of solute, I'm writing it over here. N factor of solute. And in the denominator, what do we have? We have got volume of solution in ml. Right? Now, can you understand one thing over here? If you look at this particular result, what do we call this term as? This particular term in the box is called as molarity, right? So I got to know normality of the solution is equal to molarity of the solution multiplied by n factor of solute. Multiplied by n factor of solute. This is again one important result. Whenever molarity of the solution will be given to us, if you multiply molarity of the solution by n factor of solute, you'll be getting the normality of the solution. Right? Now, people, one more thing. If you'll be having a solution whose normality will be given to us, whose volume will be given to us, can't we calculate number of gram equivalents of solute? It is simply going to be normality multiplied by volume in liters. Normality multiplied by volume in liters. So normality of the solution multiplied by volume of solution in liters. Can I say it gives me the number of gram equivalents of solute? Right? Normality of the solution multiplied by volume of solution in liters. It gives me the number of gram equivalents of solute. Now, guys, if I do one thing, if I write normality as such, instead of volume of solution in liters, if I use volume of solution in ml, then it gives me the number of milli equivalents. Be careful with all these terms. So I have got 3 results to calculate number of gram equivalents. In the similar way, I have got 3 results to calculate the number of milli equivalents. First result is in terms of mass. Second result is in terms of moles. Third result is in terms of normality. Is this clear to everyone? Can you let me know once in the chats quickly? So you have to remember these 6 results because they form the basis of your titration questions. So say it if it is clear to everyone. Just you have to remember these results. And I'll show you exactly how to apply them in the questions. One simple question I'm giving you. Simple question. Calculate the number of gram equivalents present in 50 ml of 0.5 normal NaOH aqueous solution. So as per the question, we have to calculate number of gram equivalents of solute. Number of gram equivalents of solute. Few minutes back, I told you, there are 3 ways to calculate gram equivalents. 1, in terms of mass. 2nd, in terms of moles. 3rd, in terms of normality. So it's going to be normality of solution multiplied by volume of solution in liters. Because I'm talking about gram equivalents. I'm not talking about milli equivalents. Right? Now, dear students, as far as the question is concerned, normality of the solution is given 0.5. Volume of the solution is given in ml. So convert it into liters. Divide by 1000. Now it's in liters. Now do this calculation. You're done. You got the gram equivalents of solute in the solution. Is this clear to everyone? Right? Is this clear? Simple thing, right? I was supposed to calculate the gram equivalents of solute. What did I do? Normality of the solution multiplied by volume of solution in liters. If I was supposed to calculate milli equivalents of solute, then normality multiplied by volume of solution in ml. Now guys, why was I teaching you all this? Why was I telling you to remember these results? Because of the equivalent concept which we are going to discuss now. And what this equivalent concept is all about. It's again very simple. Provided you remember n factors, provided you remember how to calculate the n factors. Now understand. For example, I've got a general reaction. A plus B, it gives C plus D. It's one general reaction. What equivalent concept says? Equivalent concept says that gram equivalence of A reacted in the reaction has to be equal to gram equivalence of B reacted, which has to be equal to gram equivalence of C formed, which has to be equal to gram equivalence of D formed. Whenever we'll be using the equivalent concept, we are not supposed to balance the reaction. No need to balance the reaction. Just write this particular statement, that's all. Gram equivalence of A reacted should be equal to gram equivalence of B reacted. That has to be equal to gram equivalence of C formed. That has to be equal to gram equivalence of D formed. Right? Basically, it's the law of equivalence. Law of equivalence states that at equivalent point, gram equivalence of A reacted in the reaction has to be equal to gram equivalence of B reacted, is equal to gram equivalence of C formed, is equal to gram equivalence of D formed. You can write the same statement in terms of milli equivalence as well. You can write, as per law of equivalence, milli equivalence of A reacted has to be equal to milli equivalence of B reacted, which has to be equal to milli equivalence of C formed, which has to be equal to milli equivalence of D formed as well. Right? Which has to be equal to milli equivalence of D formed as well. If you know how to write these two statements for a particular reaction, you can solve all the questions which can be asked in the NEET. Okay? Now, how do we solve the questions with the help of these two statements? Before that, I would want you guys to remember two n factors, which we have already discussed. Say, FeSO4. If I talk about FeSO4, in acidic medium, if FeSO4 is treated with KMnO4, when FeSO4 is treated with KMnO4 or K2Cr2O7 in acidic medium, over here iron is in Fe plus 2 state. This KMnO4 in acidic medium, if it converts Fe di positive into Fe tri positive, so change in the oxidation state comes out to be 1. So directly from now onwards, whenever you see a question in which FeSO4 is treated with KMnO4 or K2Cr2O7 in acidic medium, you'll be directly writing its n factor as 1. Number 1. If I talk about KMnO4 in acidic medium, you know it gets converted to Mn di positive. Its n factor in acidic medium is 5. These are frequently used n factors, right, which I'm writing over here. If you talk about K2Cr2O7 in acidic medium, it shows the n factor of 6. Do you remember? I've shown you all this. Similarly, for example, you have got FeC2O4. This is ferrous oxalate. When it is treated with KMnO4 or K2Cr2O7 in acidic medium, its n factor comes out to be 3. This is the compound which we discussed already. It is that compound in which oxidation state of more than one element simultaneously increases. Iron changes its oxidation state from +2 to +3. Carbon changes its oxidation state from +3 to +4. We have discussed this as well. And how do we calculate its n factor? N1 plus N2. Discuss that. Right? For example, you have got Fe2C2O4 whole thrice. Fe2C2O4 whole thrice. Now you are, for example, making this particular substance to react with KMnO4 or K2Cr2O7 in acidic medium. What will happen? Iron here is in +3 oxidation state. Right? We know KMnO4 that converts Fe di positive into Fe tri positive. But over here, iron is already in Fe tri positive. So this KMnO4 is not going to react with this iron over here because it's already in Fe tri positive state. If it was in Fe di positive, then it would have got converted. Right? So this KMnO4, it's not going to affect this Fe tri positive. But the carbon over here, it's in +3 oxidation state. And you know KMnO4, it converts oxalate ion into what? It converts oxalate ion into carbon dioxide. Right? It converts oxalate ion into carbon dioxide. So +3 to +4, change is 1. 1 is the change for one atom, but I have 6. So its n factor is 6. So directly, no need to do all these things again. We have already discussed all these. So I'll say n factor of this particular substance will be 6, right? Similarly, if I talk about sodium oxalate, Na2C2O4, right? Over here, again, you have got oxalate ion. So KMnO4 or K2Cr2O7. In acidic medium, it converts oxalate ion into carbon dioxide. And when you calculate its n factor will come out to be 2, right? For example, you have got potassium oxalate, K2C2O4. Again, its n factor you'll be taking as 2, right? For example, you have got I negative. KMnO4 as well as K2Cr2O7. In acidic medium, it converts I negative into I2, right? Perfect. And you can calculate its n factor as well. I negative into I2. So -1 to 0 changes 1. I hope you remember all these things. I hope you remember all these things. Yeah? Is it clear? Is it clear, guys? Now understand why am I telling you to remember these basic things. For example, you have got a question here. There are many ways of solving this question, but I'm showing you to solve the question with, I'll be showing you how to solve this question in very lesser time. As far as the question is concerned, what volume of 0.1 molar KMnO4? What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate? So as per the question is concerned, these two have to react basically. What volume of 0.1 molar KMnO4, right, is required to oxidize this? So these are going to react. These are the reactants here, okay? If these are the reactants, no need to write the equation, no need to balance it, just use the equivalent concept. In the equivalent concept, we are not supposed to balance the reaction. Just use the equivalent concept. But before using the equivalent concept, let's try to write all the data which is given for these two things. Understand? KMnO4. Let me represent KMnO4 by number 1. Let me represent ferrous oxalate by number 2. First of all, do you remember the n factor of KMnO4 in acidic medium? Yes, it's 5. N factor of ferrous oxalate when it is treated with KMnO4, right now, few minutes back I told you, it's 3. Yeah. Nowadays, students, what is the molarity of KMnO4 solution? Molarity of KMnO4 solution is given to me as 0.1. Volume of KMnO4 solution I need to calculate. What volume of this solution is required to oxidize? Molarity of the second solution is given to me as 0.3. And volume of the second solution is also given to me as 100 ml. Perfect. This is the data which is given to me. Now, my dear students, I'm asking you one thing. Whether volume over here is given in ml or liters, volume is given in liters, right? Should I be writing the statement which I told you a few minutes back, this particular statement, gram equivalence or milli equivalence? Should I write the statement in terms of gram equivalence or milli equivalence? What do you think? What do you think? Should I be writing the statement in terms of gram equivalence or milli equivalence? If you remember this particular result, just a second. If you remember this particular result, when we calculate gram equivalence, volume has to be in liters. When you calculate milli equivalence, volume has to be in ml, right? Now the question that has been given to us, in that question, volume is in ml. Volume is in ml. So should I be writing the statement in terms of gram equivalence or milli equivalence? I'll write the statement in terms of milli equivalence. And how exactly? I'll say milli equivalence of KMnO4 reacted has to be equal to milli equivalence of ferrous oxalate reacted. Because both are reacting only. And as far as equivalent concept is concerned, milli equivalence of this reacted has to be equal to milli equivalence of this reacted. Now, how many formulas do I have to calculate milli equivalence? 3 formulas. Mass formula, moles, millimoles formula, and normality formula. So over here, the data for normality is given. So we'll be using that only. Instead of milli equivalence of 1, I'll be writing normality of 1 multiplied by volume of 1 in ml. Milli equivalence of 2 means normality of 2 multiplied by volume of 2 in ml. Correct? Now, what is normality of 1? What is normality of 1? I'm given with the molarity of 1. I know the n factor of 1. Molarity multiplied by n factor. Does that give me the normality? So normality here is 0.5. What is the normality of second solution? Molarity multiplied by n factor. 0.3 into 3 comes out to be 0.9. Perfect. Right? Now, dear students, N1. N1 value is 0.5. V1 value I need to calculate. N2 value is 0.9. V2 value is 100. When you solve it, V1 comes out to be 180 and this volume will come out to be in ml. And this is V1 which I was supposed to calculate. So I got to know 180 ml of 0.1 molar KMnO4 is enough to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium. That's something which I was supposed to calculate. I hope you got it. Let's try to do one more question so that it becomes properly clear. Understand this particular question. What volume of 0.1 molar KMnO4? Again, I'm given with KMnO4. What volume of 0.1 molar KMnO4 is required to oxidize ferrous sulfate? Is required to oxidize 100 ml of 0.2 molar ferrous sulfate. Which concept we are using right now? Equivalent concept. In the equivalent concept, are we supposed to balance the reaction? No. It is given that these two are supposed to react. Right? Now, let's try to write the data which is given to us. Let's call this as number 1. Let's call this as number 2. Now, what volume of this? Let's say volume of this is V1, which we have to calculate. Molarity of the first solution is given to me as 0.1. N factor of KMnO4 in acidic medium is 5. V2 must be given to me, it's 100 ml, right? Molarity of the second solution is given to me as 0.2. N factor of this particular FeSO4, few minutes back, I told you, right? KMnO4, it converts Fe di positive into Fe tri positive, due to which its N factor has to be 1. Correct? Now guys, since molarity we know, N factor we know, if I multiply these two, I'll be getting normality, 0.5. Normality of second, this multiplied by this, the value is 0.2. Now, I'll be using the equivalent concept, and as far as the equivalent concept is concerned, gram equivalence of this reacted has to be equal to the gram equivalence of this reacted. Or you can write the statement in terms of milli equivalence as well. Since the volume is in ml, so I'll be preferring to write the statement in terms of milli equivalence. I'll say milli equivalence of 1 reacted has to be equal to the milli equivalence of 2 reacted. Milli equivalence of 1 will be equal to normality of 1, volume of 1 in ml is equal to normality of 2, volume of 2 in ml. Correct? Normality of 1 is 0.5. 0.5, volume of 1 we have to calculate. Normality of 2 is 0.2 and volume of 2 is 100 ml. So V1 over here will come out to be how much? It will come out to be 40 ml. Is that? 2 by 5, right? Yeah, 40 ml. So what is the meaning of this V1 which came out to be 40 ml? It means that 40 ml of 0.1 molar KMnO4 is enough to oxidize 100 ml of 0.2 molar FeSO4 in acidic medium. Done and dusted, right? Again, one simple question it was. Let's have a look on one more question. Let's have a look on one more question. Okay. Look at this question, guys. Similar type. It is a similar type question. What volume of 0.2 molar K2Cr2O7? So K2Cr2O7 is going to react with sodium oxalate, Na2C2O4 in acidic medium. Yeah. Let me call this as number 1. Let me call this as number 2. Do you remember their N factors now? N factor of K2Cr2O7 in acidic medium is 6. And N factor of sodium oxalate in acidic medium, it's 2. Right? Because this K2Cr2O7, it converts oxalate into carbon dioxide. Perfect. In oxalate, the oxidation state of carbon is +3. In carbon dioxide, it's +4. So +3 to +4 change is 1. 1 is a change for one atom, but I have 2. So its N factor is 2 basically. That's something which we have discussed already. Now, molarity of the first solution is given to me as 0.2. We have to calculate this volume. Molarity of the second solution is given to me as 0.3. And we are given with its volume as well, which is 50 ml. Correct? Now, should I be writing the statement in terms of gram equivalence or milli equivalence? Check it out. Volume is in ml. So I'll be writing the statement in terms of milli equivalence. Milli equivalence of 1 reacted has to be equal to the milli equivalence of 2. Right? So I'll be using the term N1 multiplied by V1 in ml. It has to be equal to N2 multiplied by V2 in ml. Perfect. N1 value. Okay, N1 we did not calculate. Molarity of first multiplied by N factor of first. That gives me the normality of first. So 1.2. Normality of second. Molarity multiplied by its N factor. So it comes out to be 0.6. Right? So N1 value is 1.2. V1 we have to calculate. N2 value is 0.6. V2 is 50. Right? So from here, you'll be getting the V1 value as 25 ml. So I would say 25 ml of K2Cr2O7 is enough to oxidize 50 ml of 0.3 molar sodium oxalate in acidic medium. I hope it is clear to everyone. Let's try to solve one more question. Have a look on this particular question. As far as the question is concerned, how many moles of KMnO4? How many moles of KMnO4 will be required to react completely with what? With 1 mole of potassium oxalate. So basically KMnO4 now is going to react with potassium oxalate, correct? So let me call this as number 1. Let me call this as number 2. What is the N factor of KMnO4 in acidic medium? It's 5. What is the N factor of potassium oxalate in acidic medium? It's 2. In the question, he's asking you about how many moles of KMnO4. So moles of KMnO4 we have to calculate. How many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate, right? Now over here, there is normality, etc. That's not given. The data is given with respect to moles. So should I be writing the statement in terms of gram equivalence or milli equivalence? Number of gram equivalence is equal to number of moles multiplied by N factor. Number of milli equivalence is equal to number of millimoles multiplied by N factor. The data has been given in terms of moles. So I'll prefer to write the statement in terms of gram equivalence. I'll write gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted. Now the gram equivalence of 1. There are 3 ways to calculate gram equivalence. The result in terms of mass, result in terms of moles, result in terms of normality. So here I'll be using moles wala result. So it's number of moles of 1 multiplied by N factor of 1. It's number of moles of 2 multiplied by N factor of 2. Number of moles of 1 we have to calculate. N factor of 1 is 5. Number of moles of 2 is 1. N factor of 2 is 2. So N1 value comes out to be 2 divided by 5, which is 0.4. So what does it mean exactly? What does it mean exactly? It means 0.4 moles. 0.4 moles of KMnO4 are enough to react completely with 1 mole of potassium oxalate in acidic medium. Is this clear to everyone? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Just do one thing. Add 2 more things here. Cu2s, when it's treated with KMnO4 or K2Cr2O7 in acidic medium, its N factor is 8. And Cus, when it's treated with KMnO4 or K2Cr2O7, its N factor is 6. Right? Just note them up. We have discussed these also when we spoke about the N factors. Okay, say in the chats if all the things are clear. Quickly. Look at one more similar type of question. One more similar type of question. How many moles of KMnO4? Again, we have to calculate moles. Sorry, how many moles of K2Cr2s are required to react completely with 2.5 moles of Cu2s? Let me call this as number 1. Let me call this as number 2. What is the N factor of K2Cr2O7 in acidic medium? 6. N factor of Cu2s in acidic medium? It's 8. Right? How many moles of K2Cr2O7? Moles of K2Cr2O7 I have to calculate. Moles of Cu2s are given to me as 2.5, right? So since the data related to moles is given to us, so I'll be preferring to write the statement in terms of moles. I'll write gram equivalence of 1 reacted should be equal to gram equivalence of 2 reacted. And gram equivalence of 1 right now I'll write as number of moles of 1 multiplied by N factor of 1. This is number of moles of 2 multiplied by N factor of 2. Number of moles of 1, I need to calculate. N factor 1 is 6. Number of moles of 2, that's 2.5. N factor of 2, that's 8. So N1 value you can calculate from here. It's 8 divided by 6 multiplied by 2.5. Solve it, get the answer. Right? Is this clear to every single guy? Yes? I hope you can easily solve these questions now. I hope you can easily solve these questions now. Look at this one. 6 moles of AN positive. 6 moles of AN positive. Requires 2 moles of Cr2O7 dinegative. Requires 2 moles of Cr2O7 dinegative. for the oxidation of An positive to AO3 negative. To AO3 negative. In acidic medium. And we know in acidic medium, Cr2O7 di negative, it gets converted into Cr tri positive. The value of N will be. So we have to get the value of this N. This is the reaction, right? This is the reaction. As far as the question, again, let me call this as number 1. Let me call this as number 2. Okay? Number 1, number 2. How many moles of An positive are we given with? 6. How many moles of Cr2O7 di negative are we given with? 2. What is the N factor of Cr2O7 di negative? Have a look. Plus 6 to plus 3. Change is 3. 3 is the change for one atom, but I have 2. So it's 6. If I ask you, what is the N factor of An positive? Plus N to plus 5. Plus 5 is the oxidation state of A. Here the oxidation state of A is plus N. So plus N to plus 5. Changes final minus initial. So final minus initial come mod. Right? Final minus initial. Now, if you use the equivalent concept says gram equivalence of 1 has to be equal to gram equivalence of 2. Gram equivalence of 1 will be number of moles of 1 multiplied by N factor 1 is equal to number of moles of 2 multiplied by N factor of 2. Number of moles of 1 is 6. N factor of 1 is 5 minus N, right? N2 is 2, N factor 2 is 6. So 6 and 6 got cancelled. N value came out to be 3. And that N, what is that N? N is basically the charge present on A. So A is actually present in tri-positive state. This is something which I was supposed to calculate. Is this clear? Is this clear to everyone? Quickly. For example, I'm giving you a question like this. The question is, how many moles of KMnO4 are required to react with a mixture containing 1 mole each of FeSO4, FeC2O4, Fe2C2O4 whole thrice. Then it's going to be Fe2SO4 whole thrice in acidic medium. Let's say this is one question. Let's say this one question. Let me see if you can solve this one or not. It's again a simpler one, guys. Just understand what I'll be doing. Imagine that you have got a container and that container contains FeSO4. With FeSO4, you have got FeC2O4. With FeC2O4, we have got Fe2C2O4 whole thrice. And with this, you have got Fe2SO4 whole thrice. Let's say we have got a container and that container contains 1 mole of FeSO4, 1 mole of this particular thing, 1 mole of this particular thing, and 1 mole of this particular thing, right? Now, as per the question is concerned, this is, for example, the container that contains a mixture of these things, right? Now, as far as the question, you are introducing KMnO4 in this one. And the reactions have to be taken place in acidic medium, right? The reaction has to participate in the acidic medium. You are introducing KMnO4. Now, first of all, you need to see the KMnO4 which you are adding, whether it's going to react with all or not. See, over here, iron is in di-positive state and KMnO4 converts Fe di-positive into Fe tri-positive. So KMnO4 is going to react with the first one. In the second one, iron is in di-positive. So plus 2 to plus 3. The oxalate here, it converts oxalate into carbon dioxide. That means KMnO4 is going to react with this one as well. KMnO4 will be reacting with this one as well because here again you have got oxalate. It converts oxalate into carbon dioxide. But right here, iron is in tri-positive state. So KMnO4 is going to do nothing with this Fe tri-positive. It is just going to convert this oxalate into carbon dioxide, right? Over here, iron is in plus 3, sulfur is in plus 6. What is KMnO4? It is the oxidizing agent. It oxidizes others. But over here, iron as well as sulfur, they are present in their maximum oxidation states. They are present in their maximum oxidation states. So KMnO4 cannot increase the oxidation state of iron beyond +3. It cannot increase the oxidation state of sulfur beyond +6. They are already in maximum oxidation states. So KMnO4, which is the oxidizing agent, which has to oxidize others. So KMnO4 is not going to react with this one. Right? KMnO4 is not going to react with this one. Because here both the elements are present in their maximum oxidation state. KMnO4 cannot increase their oxidation state beyond their maximum value. Yeah? So the KMnO4 which you are adding, it's going to react with these three things. So what is the statement which I'll be writing? Okay, before the statement, tell me the N factor of FeSO4, it's 1. Tell me the N factor of ferrous oxalate, it is 3. Tell me the N factor of ferric oxalate, it is 6. Right? These are the N factors. Now, after writing the N factors, the statement has to be KMnO4 has to react with these three. So I'll say gram equivalence of 1 reacted plus gram equivalence of 2 reacted plus gram equivalence of 3 reacted has to be equal to gram equivalence of KMnO4. Perfect. Now write the things. Gram equivalence of first means number of moles of first multiplied by N factor of first. So 1 plus gram equivalence of 2. Moles of 2 multiplied by N factor of 2. So 3 plus gram equivalence of 3. 6 into 1 is 6 is equal to gram equivalence of KMnO4. Moles of KMnO4, which we have to calculate, multiplied by N factor of KMnO4 in acidic medium. N factor of KMnO4 in acidic medium. So one equation, one unknown. 6, 3, 9 plus 1, 10. 10 divided by 5 is 2. So basically, I got to know the number of moles of KMnO4 here as 2. So what this 2 exactly means now? It means 2 moles of KMnO4 is enough to oxidize this particular mixture which we have, right, in acidic medium. Is this clear to everyone? So first of all, you need to check whatever species you are adding, whether it's going to react with all or not. If it is not reacting with all, like this, it's not reacting with this one. I've got nothing to do with this one. I'll say gram equivalence of this plus this plus this has to be equal to the gram equivalence of the agent which we have added. I hope this is clear to everyone. And these sort of questions are asked in your NEET examination basically, which are pretty much simple, right? There are some more questions, but they are of JEE standard. I'm sure you won't like them, nor will they be asked in your examination. This question has to be your homework. Okay, this is your homework question. You are going to let me know the answer of this particular question in the comment section at the end. I hope all these questions which can be asked from the equivalent concept, I hope they are clear. You can solve them, right? Now we can try out any module which you have, any practice book which you have. Just try to solve the questions. I'm damn sure you can easily solve all the questions from the Redox. Okay. There is one topic that's left, that is volume strength, but let's do it some other time, okay? So when I'll teach you electrochemistry, in electrochemistry, I'll teach you volume strength. Perfect. I think all the things are clear. Yeah. I think whatever we discussed, everything is clear, right? Perfect. The questions which I gave you as the homework, give them a try and do let me know their answers as well in the comments. So people, with this, we are done with the redox reaction. One topic, volume strength, that's something I'll be teaching you in electrochemistry. Yeah. PDF of this particular one, I'll be sharing in the Telegram group. You know the Telegram ID, right? t.me/WASSIMSIRCHEM. Okay. So with this, I'll be taking a leave. Let's meet for the next chapter. The next chapter is going to be solid state, which will happen day after tomorrow. Day after tomorrow, we'll be doing the chapter solid state. Hello. Take care then. See you all. Bye-bye. Hope you enjoyed the session.